Hello and welcome. I'm glad you're here. Tonight we're going to explore something so fundamental, so woven into the fabric of existence, that we rarely stop to think about it. Gravity. The gentle force that keeps your head on the pillow, that pulls the blanket down around your shoulders, that holds the moon in its patient orbit around Earth. It's the quietest of the universe's forces, and yet it shapes everything, from the fall of an apple to the spiral of galaxies, from the rhythm of tides to the curvature of space-time itself. We'll wander through 100 facts about gravity tonight, moving from the simple to the strange, from what Newton observed in his garden to the mysteries that still keep physicists awake at night. But there's no rush. Let these ideas wash over you like waves. Some will catch your attention. Others will simply drift past, and that's perfectly fine. This isn't a test. It's an invitation to wonder. Before we begin, if you enjoy falling asleep to science, if you like the idea of learning while you drift, consider subscribing to the channel. It helps us keep making these journeys into the cosmos for you, night after night. Now, let's begin. Gravity is the weakest of the 4 fundamental forces in nature, yet it shapes the entire structure of the cosmos. There are 4 fundamental forces that govern everything in the universe. The strong nuclear force, which binds the hearts of atoms together. The weak nuclear force, responsible for certain types of radioactive decay. Electromagnetism, which creates light and holds molecules together. And gravity. Of these 4, gravity is by far the weakest. How weak? Well, consider this. Right now, a small refrigerator magnet can lift a paperclip off your desk. That tiny piece of metal, using electromagnetic force, overcomes the gravitational pull of the entire planet Earth. All of Earth, every mountain, every ocean, every bit of iron in the core, pulling down on that paperclip, and a magnet the size of your thumb can defeat it. And yet, despite this weakness, gravity is the force that organizes the cosmos. It gathers clouds of hydrogen into stars. It binds stars into galaxies. It curves the very fabric of space-time. The other forces are stronger, yes, but they're also short-ranged, or they cancel themselves out. Gravity is patient. Gravity is persistent. It reaches across the void and pulls everything together. Slowly, inevitably. In its gentleness lies its power. Perhaps that's something to remember as you drift off tonight, that the quietest things can shape the most. Isaac Newton never actually saw an apple fall from a tree. That story was embellished decades after his death. The story is famous, almost mythic. Young Isaac Newton, sitting beneath an apple tree, watches an apple fall, and in that moment gravity is discovered. It's a beautiful story. It's also not quite true. What Newton actually did was far more interesting. He didn't just wonder why the apple fell. Everyone knew things fell. He wondered why the moon didn't fall. He looked up at the moon, hanging there in the sky, and asked himself a question that changed everything. If gravity pulls the apple down, why doesn't it pull the moon down too? And then he realized, it does. The moon is falling. It's falling toward Earth right now. And it has been for billions of years. It's just that the moon is also moving sideways so fast that as it falls, it keeps missing the Earth. It falls around the planet in an endless, graceful arc. An orbit is just falling sideways forever. There may have been an apple. there may have been a garden. But the real insight wasn't about things falling down. It was about understanding that falling down and orbiting around are the same thing, seen from different perspectives. Sometimes the stories we tell about science are simpler than the truth, because the truth is more wonderful than we know how to say simply. Gravity isn't actually a force pulling you down. It's the curvature of space-time pushing you along the straightest possible path. For centuries we thought of gravity as a force, something invisible reaching out across space, pulling masses toward each other. Newton described it mathematically, predicted it, used it to chart the paths of planets. But he never claimed to understand what it actually was. "I frame no hypotheses," he wrote. "It worked. That was enough." Then Einstein came along and said, "What if gravity isn't a force at all? What if, instead, mass curves the space around it, curves space-time itself, and objects simply follow the straightest possible path through that curved geometry? You're not being pulled toward the Earth. You're moving through space-time that's been bent by Earth's mass, and the straightest path through that bent space happens to look, from your perspective, like falling. Imagine a marble rolling across a stretched rubber sheet. Now place a bowling ball in the middle of that sheet. The sheet curves, the marble rolling nearby will curve toward the bowling ball, not because the bowling ball is pulling it, but because the surface itself is curved. That's gravity. Not a pull, but a push. Not a force, but a shape. You are right now following the curvature of space-time. The path feels natural because it is natural. It's the geometry of reality, and you're simply moving through it, like water finding its way downhill, not because something pulls the water, but because down is the shape the world has made. The strength of gravity decreases with the square of the distance, meaning if you double your distance from something, gravity becomes 4 times weaker. There's an elegant simplicity to the way gravity fades. It's called the inverse square law, and it applies to anything that spreads out evenly in space: light, sound, gravity. The rule is this: double the distance, and the strength drops to 1/4. Triple the distance, and it drops to 1/9. Why? Because gravity spreads out in 3-dimensional space. Imagine the gravitational influence of the Earth as an invisible sphere, expanding outward. As that sphere grows, the same amount of gravitational influence has to cover a larger and larger surface area. The surface area of a sphere grows with the square of the radius, so gravity weakens with the square of the distance. This is why astronauts, just a few hundred miles above Earth's surface, can float freely. They haven't escaped Earth's gravity, far from it. Earth's gravity is still strong enough to hold the Moon in orbit, and the Moon is 250,000 miles away. But at the altitude of the International Space Station, gravity is about 90% as strong as it is on the surface. Yeah, they float not because there's no gravity, but because they're in free fall, constantly falling around the planet. Distance matters. It's the reason we can have stable orbits, the reason tides rise and fall, the reason the universe is structured the way it is. Gravity's reach is infinite, but its strength is not. It fades gently, persistently, across the cosmos, connecting everything but loosening its grip the farther you go. Every object with mass creates its own gravitational field, including you. Right now, As you lie there, you're pulling on everything around you. The walls, the ceiling, the moon, the distant stars. Your mass, however small in cosmic terms, curves space-time, and that curvature extends outward in all directions, weakening but never quite vanishing. The force is incomprehensibly tiny, of course. Your gravitational pull on another person standing across the room is far weaker than the breeze from an open window, but it's there. It's real. You are connected gravitationally to every atom in the universe, and they are pulling back. The sun is pulling on you right now, even though it's 93 million miles away. Jupiter is pulling on you. Andromeda, our neighbouring galaxy, 2.5 million light years distant, is pulling on you. The pull is unimaginably faint, but it exists. Gravity has no off switch. It has no shielding. If you have mass, you create gravity, and you respond to gravity, and you are woven into the gravitational fabric of everything. Perhaps that's a comforting thought. You're not separate from the cosmos. You're part of it, pulling and being pulled, a participant in the vast, gentle choreography of space-time. Even in stillness, you are connected. Galileo demonstrated that all objects fall at the same rate in a vacuum, regardless of their mass. Before Galileo, the prevailing wisdom, inherited from Aristotle, was that heavier objects fall faster than lighter ones. It made intuitive sense. Drop a rock and a feather, and the rock reaches the ground first. Clearly the rock falls faster. But Galileo wasn't satisfied with intuition. He reasoned that if you removed air resistance, the feather and the rock should fall at the same rate. Why? Because gravity pulls on all objects equally, relative to their mass. A heavier object experiences more gravitational force, yes, but it also has more inertia, more resistance to acceleration. The two effects cancel out perfectly. He couldn't create a vacuum in his time, so he tested the idea with inclined planes, and rolling balls of different masses down ramps. They accelerated at the same rate. Centuries later, astronauts on the moon, where there's no air, dropped a hammer and a feather side by side. They landed simultaneously, just as Galileo predicted. It's a simple experiment, but it reveals something profound. Mass doesn't matter to gravity in the way we might expect. Gravity doesn't care if you're a speck of dust or a planet. The acceleration is the same, only the air gets in the way. Remove the air, and a feather falls like a stone. Maybe there's something poetic in that. The idea that stripped of resistance, all things fall together equally. Earth's gravity varies slightly depending on where you stand. You weigh less on a mountain than at sea level. You might think of gravity as a constant, the same everywhere on Earth's surface. But Earth isn't a perfect sphere. It's slightly flattened at the poles and bulges at the equator. Mountains rise, ocean trenches sink. The density of rock varies from place to place. All of this means that gravity changes subtly, depending on where you are. At the top of Mount Everest, you weigh about 0.5% less than you would at sea level. Why? Because you're farther from the center of the Earth, and gravity weakens with distance. Conversely, in a deep mine, you'd weigh slightly less too, because some of Earth's mass is now above you, pulling you upward ever so slightly. You also weigh a bit less at the equator than at the poles. 2 reasons. First, Earth's rotation creates a centrifugal effect that pushes outward, counteracting gravity slightly. Second, the equatorial bulge means you're farther from the center of the planet. These differences are tiny, imperceptible without precise instruments, but they're there. Gravity is not uniform, it's textured, shaped by the planet's geology, its spin, its imperfections. Even standing still, you're experiencing a subtly different universe than someone standing elsewhere. The ground beneath you has its own gravitational fingerprint. The tides in our oceans are caused by the moon's gravity pulling more strongly on the side of Earth closest to it. Twice a day the ocean rises. Twice a day it falls. The rhythm of tides is written into coastal life, into navigation, into the biology of creatures that live between land and sea. And it's all because of the moon. The moon's gravity pulls on the Earth, but it doesn't pull evenly. The side of Earth facing the moon feels a stronger pull than the center of the planet, because it's closer. And the center of the planet in turn feels a stronger pull than the far side. This difference in gravitational strength, this gradient, is called a tidal force. The water on the side facing the moon gets pulled toward it, creating a bulge. But here's the strange part. There's also a bulge on the opposite side of Earth. Why? Because the Earth itself is being pulled more than the water on the far side. The planet, in a sense, is being pulled away from that far water, leaving it behind. So there are two tidal bulges, one facing the moon and one facing away. As Earth rotates beneath these bulges, any given coastline experiences 2 high tides and 2 low tides each day. The sun contributes too, though less strongly. When the sun and moon align, during new and full moons, their tidal forces add together, creating especially high and low tides called spring tides. When they're at right angles, their forces partially cancel, creating gentler neap tides. The ocean breathes in rhythm with the moon. It's been doing so for billions of years, and it will continue long after we're gone. Without gravity, atoms would never have clumped together to form stars, planets, or you. In the beginning, or as close to the beginning as we can meaningfully speak of, the universe was almost perfectly smooth. Almost. There were tiny fluctuations, quantum ripples in the density of matter, variations of 1 part in 100,000. And then gravity went to work. Wherever the density was even slightly higher, gravity pulled more matter in. The denser regions became denser still, pulling in even more. This process, called gravitational collapse, is a runaway feedback loop. Over millions of years, those tiny ripples grew into vast structures. Gas clouds condensed into stars. Stars gathered into galaxies. Galaxies clustered into superclusters. Without gravity, the universe would be a thin, cold, expanding fog of hydrogen and helium, growing ever more diffuse, forever. No stars to forge heavier elements, no planets for these elements to form, no chemistry, no life, no consciousness to wonder about it all. Gravity is the architect of complexity. It's the force that fights against entropy, at least locally, pulling scattered matter into dense, interesting configurations. Every atom in your body was once part of a diffuse cloud, and gravity is what brought it all together. First into a star that fused hydrogen into heavier elements, then into a new cloud, then into the sun and earth, and eventually, improbably, into you. Gravity is patient. It works slowly. But given enough time, it builds worlds. Einstein's theory of general relativity, published in 1915, completely reimagined what gravity is. For more than 2 centuries, Newton's description of gravity worked beautifully. It predicted planetary orbits, explained tides, guided artillery shells. But it had a gap at its heart. Newton described how gravity behaved, but he couldn't explain what it actually was. Action at a distance. The idea that the sun could somehow reach across 93 million miles of empty space and pull on the Earth seemed almost magical. Einstein couldn't accept that. He spent years thinking about gravity, about acceleration, about the nature of space and time, and in 1915 he published his answer: general relativity. Gravity, Einstein said, is not a force, it's geometry. Mass and energy curve the fabric of space-time, and objects move along the straightest path through that curved space. What we experience as the pull of gravity is actually just the natural motion through a curved universe. It was a radical reimagining. Space and time were no longer a passive stage on which events unfolded. They were dynamic, malleable, shaped by the matter and energy within them. And this wasn't just philosophy. General relativity made predictions that Newton's theory couldn't. It explained the odd precession of Mercury's orbit. It predicted that gravity would bend light. It suggested the existence of black holes and gravitational waves. And over the past century, every prediction has been confirmed. Einstein's vision of gravity as geometry is, as far as we can tell, the way the universe actually works. Space curves, time dilates, and we move through it all, following paths written in the shape of reality itself. Time runs slower in stronger gravitational fields, a phenomenon called gravitational time dilation. Time, it turns out, is not the steady, universal metronome we once thought it was. It's flexible, malleable, and gravity bends it. According to general relativity, the stronger the gravitational field you're in, the slower time passes for you relative to someone in a weaker field. This isn't an illusion or a measurement error. Time actually runs at different rates depending on where you are in a gravitational field. Your feet, right now, are experiencing slightly stronger gravity than your head because they're closer to the center of the Earth. The difference is minuscule. We're talking about a distance of maybe 6 feet, but it's real. Over the course of your lifetime, your feet will age perhaps 100 nanoseconds less than your head. Not enough to notice, certainly, but enough to be true. Near more extreme gravitational fields, the effect becomes dramatic. Near a black hole, time slows so much that someone watching from a safe distance would see you move in slow motion as you approach the event horizon. From your perspective, time feels normal, but to the outside universe, you're gradually freezing in place, asymptotically approaching the edge of the black hole, never quite reaching it. GPS satellites experience this too, in reverse. They orbit high above Earth where gravity is weaker, so time runs faster for them than it does for us on the surface. If we didn't account for this time dilation, GPS coordinates would drift by kilometers within a single day. Einstein's equations are what keep your navigation accurate. Time is woven into the fabric of space-time, and gravity tugs on that fabric, stretching time itself. In a very real sense, gravity doesn't just tell you where you are, it tells you when you are. GPS satellites must account for both gravitational time dilation and the effects of their orbital speed to remain accurate. The global positioning system is quietly a testament to Einstein's genius. Every GPS satellite is a flying clock, broadcasting the time with extraordinary precision. Your device receives signals from multiple satellites, compares the timestamps, and calculates your position based on how long each signal took to arrive. But there's a problem. Those satellites are moving fast, about 14,000 kilometers per hour, and according to Einstein's special relativity, moving clocks tick slower. At the same time, they're orbiting about 20,000 kilometers above Earth's surface, where gravity is weaker, so according to general relativity, their clocks tick faster. These two effects work in opposite directions. The speed effect causes the satellite clocks to lose about 7 microseconds per day. The gravitational effect causes them to gain about 45 microseconds per day. The net result? Satellite clocks run about 38 microseconds faster each day than clocks on Earth's surface. That might not sound like much, but light travels about 300 meters in a single microsecond. Without correcting for relativity, GPS would accumulate errors of about 10 kilometers per day. Within a week, it would be useless. So every GPS satellite has relativistic corrections built into its timekeeping. Engineers program them to tick at a different rate, specifically slower, so that once they're in orbit, experiencing both time dilation effects, they sync up perfectly with Earth-based time. You're navigating through curved space-time every time you use a map on your phone. Einstein's equations are running in the background, invisible, essential. It's a strange and wonderful thing that the structure of reality itself has to be accounted for just to tell you how to get to the grocery store. Gravity travels at the speed of light, creating ripples in space-time called gravitational waves. For a long time, we didn't know how fast gravity propagates. Newton's theory didn't address it. Gravity simply existed everywhere, simultaneously. But Einstein's relativity demanded that nothing, not even information about gravity, can travel faster than light. So what happens if the sun suddenly disappeared? Would Earth immediately fly off into space, or would there be a delay? Einstein's answer: there would be a delay. For about 8 minutes, the time it takes light to travel from the sun to Earth, we'd continue orbiting as if nothing had changed. Then, all at once, we'd feel the gravitational shift. The sun's disappearance would send a ripple through space-time, a gravitational wave, propagating outward at the speed of light. These waves are real. When massive objects accelerate, particularly when they orbit each other or collide, they create ripples in the fabric of space-time itself. These ripples spread outward, stretching and squeezing space as they pass. For most of the century after Einstein predicted them, gravitational waves remained theoretical. They were too weak to detect. But on September 14th, 2015, exactly 100 years after Einstein published general relativity, humanity detected them for the first time. 2 black holes, more than 1 billion light-years away, had spiraled into each other and merged. The collision sent gravitational waves rippling across the universe. When those waves reached Earth, they stretched and compressed space by a distance smaller than the width of a proton. But we caught them. We heard the universe ringing. Gravity isn't instantaneous. It moves. It flows through space-time at the cosmic speed limit, carrying information about distant events. The universe speaks in many languages: light, particles, fields, and now, finally, we're learning to hear it speak in gravity too. The first direct detection of gravitational waves occurred on September 14th, 2015, exactly 100 years after Einstein predicted them. There's a certain poetry to the timing. Einstein published general relativity in 1915. 1 century later, to the year, LIGO, the Laser Interferometer Gravitational Wave Observatory, detected the first direct evidence of gravitational waves. LIGO consists of 2 enormous L-shaped detectors, one in Louisiana and one in Washington state. Each arm is 4 kilometers long. Lasers bounce back and forth along these arms, measuring their lengths with astonishing precision. When a gravitational wave passes through, it stretches space in one direction and compresses it in the other, causing a minuscule change in the arm lengths. How minuscule? The change is about 1/10,000th the width of a proton. To put that in perspective, if the distance between the Earth and the nearest star were the length of LIGO's arm, the gravitational wave would change it by the width of a human hair. On that September morning, both detectors registered the same signal, 7 milliseconds apart, the time it takes a gravitational wave to travel from Louisiana to Washington. The signal was brief, a chirp lasting only a fraction of a second, but it matched perfectly the predicted waveform from 2 black holes spiraling together and merging. The black holes were massive, 36 and 29 times the mass of the Sun. Their collision released more energy in gravitational waves for that brief moment than all the stars in the observable universe combined. The merger happened 1.3 billion years ago. Then the waves travelled through expanding space for over 1 billion years, and on September 14th, 2015 they passed through Earth. We are now listening to the universe in an entirely new way. Einstein was right, and after a century of waiting, we finally heard what he predicted. Gravitational waves caused by distant cosmic events pass through your body constantly, stretching and squeezing you by less than the width of an atomic nucleus. Right now, as you lie there, gravitational waves are passing through you. Waves from colliding black holes billions of light years away. Waves from merging neutron stars in distant galaxies. Waves from the violent deaths of massive stars. The universe is full of them. Ripples in space-time propagating in all directions, crisscrossing the cosmos. As each wave passes, it stretches you in one direction and squeezes you in another. The effect alternates, oscillating perhaps hundreds of times per second. But the amplitude is incomprehensibly small, far, far less than the diameter of an atomic nucleus. You will never feel it. Your body's atoms don't even notice. And yet it's happening. You are being reshaped, constantly, by events that occurred millions or billions of years ago in places unimaginably distant. The universe is ringing with the echoes of ancient collisions, and these echoes pass through you as easily as they pass through empty space. There's something humbling about that. We think of ourselves as separate, isolated, contained within our skin. But we're permeable to the cosmos. Neutrinos from the sun stream through you by the billions every second. Cosmic rays from supernovae strike your cells. And gravitational waves, the flexing of space-time itself, wash over you continuously, connecting you to events you'll never see, in places you'll never visit. The universe is not something out there. It's here, moving through you, right now. You're not an observer standing outside the cosmos. You are part of it, woven into its structure, resonating with its distant rhythms. In zero gravity, flames burn in spheres rather than the teardrop shapes we see on Earth. Fire, as we know it, is shaped by gravity. When you light a candle, the flame heats the air around it. Hot air is less dense than cool air, so it rises, pulled upward by buoyancy. Cooler air rushes in from the sides to replace it, feeding the flame with fresh oxygen. This creates the familiar teardrop shape, pointed at the top, wider at the base, flickering as currents shift. But remove gravity, and everything changes. In the microgravity environment of the International Space Station, astronauts have lit candles and watched what happens. Without gravity to create buoyancy, there's no up for hot air to rise toward. Convection stops. The flame doesn't flicker. Instead, it burns as a perfect sphere, fed by oxygen diffusing inward from all directions equally. The sphere is dimmer than an Earth flame, almost blue, because combustion is less efficient without convection to carry away exhaust gases and bring in fresh oxygen. Eventually, the flame can even extinguish itself, choking on its own carbon dioxide. It's a simple experiment, but it reveals how deeply gravity is woven into everyday experience. Fire doesn't naturally want to be teardrop-shaped. That's just what happens when gravity organizes the flow of air. Remove gravity, and fire becomes something different, quieter, stranger, more symmetric. Even something as familiar as a candle flame is shaped by forces we rarely think about. Change the gravitational context, and the universe reveals new behaviors, hidden possibilities that were there all along, just waiting for the right conditions to emerge. Your spine expands in zero gravity because there's no gravitational compression, making astronauts about 2 inches taller in space. On Earth, gravity is constantly pressing down on you. Your spine, composed of vertebrae separated by soft gel-like discs, is compressed by the weight of your own body. The discs flatten slightly, like cushions under pressure, over the course of a day. This compression can make you a bit shorter by evening than you were in the morning. Sleep horizontally and your spine decompresses overnight, and you wake up slightly taller. Now imagine removing gravity entirely. In space, astronauts experience microgravity. Their spines are no longer compressed by their body weight. The discs expand, filling with fluid stretching out. Over the course of a few days in orbit, astronauts grow about 2 inches taller. Some report back pain as their spines adjust to this new configuration. It sounds wonderful at first, instant height gain. But it comes with downsides. The muscles and ligaments supporting the spine aren't accustomed to this elongation. When astronauts return to Earth, gravity reasserts itself, and the spine compresses again within hours or days. The readjustment can be uncomfortable, even painful. There's also concern about long-term effects. Spending months in microgravity, as astronauts do on the International Space Station, can weaken the muscles and bones that normally support the spine. Future missions to Mars will need to address this, perhaps with centrifugal artificial gravity or rigorous exercise regimens. Even your height, something that seems so fixed, is negotiable. You are, in a very real sense, shaped by the gravitational field you inhabit. Change the field, and your body changes too. We are creatures of Earth's gravity, built for 1G, and leaving that environment reveals just how finely tuned we are to it. The moon is slowly drifting away from Earth at about 3.8 centimeters per year due to tidal forces. The moon is leaving us, not quickly. It will take billions of years, but it's happening measurably, just right now. The cause is tidal friction. The moon's gravity raises tides in Earth's oceans, and as Earth rotates beneath these tidal bulges, friction converts some of Earth's rotational energy into heat. This slows Earth's rotation ever so slightly, lengthening the day by about 1.7 milliseconds per century. But energy is conserved. The rotational energy Earth loses is transferred to the moon's orbit, causing the moon to spiral outward, moving to a higher, slower orbit. Currently, the moon recedes at about 3.8 centimeters per year, roughly the rate your fingernails grow. This means that billions of years ago the moon was much closer. Early in Earth's history, when the moon first formed from the debris of a massive collision, it may have orbited at a distance of only 15,000 miles, less than 1/20th its current distance. The moon would have loomed enormous in the sky, and the tides it raised would have been catastrophic, hundreds of feet high. Back then, Earth's day was only about 5 hours long. The moon orbited faster. Everything was spinning, churning, chaotic. Over billions of years, tidal forces have gradually calmed the system, slowing Earth's rotation and pushing the moon away. Eventually, in the far future, the moon will recede to a point where Earth's rotation and the moon's orbit are synchronized. Earth will become tidally locked to the moon, always showing the same face, just as the moon already shows the same face to Earth. The dance will reach equilibrium, and the moon will drift no farther. But that's billions of years away. For now, every night the moon moves a little farther from us, imperceptibly, inevitably. Yes, gravity assists allow spacecraft to gain speed by borrowing momentum from planets they fly past. Imagine you're on a skateboard and a truck drives by. You reach out and grab the back of the truck. The truck pulls you forward and you accelerate. From your perspective, you've gained speed. But here's the thing, the truck slows down very, very slightly because you're pulling back on it. Momentum is conserved. You borrowed speed from the truck. Spacecraft do the same thing with planets, using a technique called a gravity assist or gravitational slingshot. The Voyager probes, launched in 1977, and now the most distant human-made objects in the universe, used gravity assists from Jupiter and Saturn to reach speeds impossible with rockets alone. As Voyager approached Jupiter, it fell into the planet's gravitational well, accelerating. But instead of crashing or orbiting, it swung around the backside and flew away in a new direction. From Jupiter's perspective, Voyager approached, looped around and left at the same speed it arrived. But from the Sun's perspective, from the larger reference frame, Voyager stole some of Jupiter's orbital momentum. It left faster than it arrived. The amount of momentum Jupiter lost is infinitesimal. The planet didn't even notice. But for Voyager it was transformative. Each gravity assist added kilometers per second to its velocity, allowing it to reach the outer planets and eventually escape the solar system entirely. It's a beautiful trick, really. A spacecraft with no fuel, no engine firing, gains speed simply by falling past a planet in the right way. Gravity, shaped by the planet's motion, flings the spacecraft forward. It's like surfing on the gravitational currents of the solar system, riding the invisible flow of space-time's curvature. At the exact center of Earth, you would be weightless, because gravity pulls equally in all directions. Imagine drilling a hole straight through the Earth, all the way to the center. Ignore the heat, the pressure, the impossibility of it. Just imagine you could travel down this hole, falling toward the core. As you fall, you'd accelerate, pulled by Earth's gravity. But something strange would happen as you approached the center. The gravity pulling you downward would weaken. Why? Because more and more of Earth's mass is now above you, pulling you back up. At the exact center, the geometric middle of the planet, you'd be surrounded equally by mass in all directions. Every atom of Earth would be pulling on you, but the pulls would cancel out perfectly. The net gravitational force on you would be zero. You'd be weightless, floating, suspended in equilibrium. Of course, you wouldn't stay there. Weightlessness doesn't mean motionlessness. If you had any velocity at all, you'd drift past the center and start falling toward the opposite side. You'd oscillate back and forth through the center like a pendulum passing through its lowest point, gradually slowing due to air resistance, if there were air, until you eventually settled, motionless, at the core. It's a strange thought. A bubble of weightlessness at the heart of the planet, surrounded by unimaginable pressure and heat. The very center of Earth's gravitational field is a place where gravity's pull paradoxically disappears. There's a metaphor in there, maybe. Or sometimes the strongest forces create at their very center a stillness. Neutron stars have gravity so intense that a sugar cube-sized piece of their matter would weigh 1 billion tons on Earth. When a massive star dies, its core can collapse into something almost unimaginable, a neutron star. These are objects about 20 kilometers across, roughly the size of a city, but containing more mass than the Sun. The density is beyond comprehension. Take a sugar cube. A single sugar cube of neutron star material would weigh about 1 billion tons. That's the mass of Mount Everest, compressed into something you could hold between your fingers. If you somehow brought it to Earth, if you could even hold it, which you couldn't, it would instantly plunge through the ground, through the crust, through the mantle, all the way to the core, its gravity pulling everything nearby along with it. The gravity at the surface of a neutron star is about 200 billion times stronger than Earth's. If you could stand on one, and you absolutely couldn't, you'd be flattened instantly. Not crushed exactly. Flattened. Your atoms would be pressed into a layer thinner than the width of an atom itself. The tidal forces alone would rip you apart long before you touched the surface. Neutron stars are matter in extremis. Protons and electrons are squeezed together so tightly that they merge into neutrons, and even the neutrons are packed as densely as the nucleus of an atom. It's matter at the edge of what physics allows before it collapses further into a black hole. And yet neutron stars exist. We've detected thousands of them, spinning rapidly, beaming radiation across space like cosmic lighthouses. They're real. They're out there. Objects so dense, so strange, that they challenge our intuition about what matter can be. The escape velocity from Earth's surface is about 11.2 kilometers per second, or roughly 25,000 miles per hour. If you throw a ball upward, it eventually falls back down. Throw it harder, and it goes higher before returning. But throw it hard enough, impossibly hard, and it will never come back. It will escape Earth's gravity entirely. That threshold speed is called escape velocity. For Earth, it's about 11.2 kilometers per second, or 25,000 miles per hour. Anything travelling that fast or faster aimed upward will leave Earth and never return unless something else slows it down. This is why rockets need to be so powerful. They're not just lifting mass against gravity, they're accelerating that mass to escape velocity, and they have to do it while fighting air resistance and carrying their own fuel, which adds weight, which requires more fuel, which adds more weight. It's a brutal equation. Interestingly, escape velocity doesn't depend on the mass of the object escaping. A feather and a rocket need the same speed to escape Earth's gravity. What differs is the energy required to accelerate them to that speed. A feather requires far less energy, but the speed itself is the same. The Moon's escape velocity is much lower, only about 2.4 kilometers per second, because the Moon is less massive and smaller. This is why the Apollo astronauts needed relatively small rockets to leave the lunar surface and return to Earth. Black holes, by definition, are objects where the escape velocity exceeds the speed of light. Once you're inside the event horizon, not even light travels fast enough to escape. The threshold has been crossed. There is no throwing hard enough, no engine powerful enough. The exit is closed. Black holes represent regions where gravity has become so extreme that not even light can escape. A black hole is a region of space-time where gravity has won completely. Matter has collapsed to such density that the escape velocity exceeds the speed of light, and since nothing can travel faster than light, not matter, not information, not even light itself, nothing that falls in can ever come back out. The boundary of no return is called the event horizon. It's not a physical surface. You could pass through it without feeling anything unusual, at least initially. But once crossed, all your possible futures lead inward. Every path through space-time, no matter which direction you try to move, curves inexorably toward the center. Outside the event horizon, you could still escape if you had a powerful enough rocket. Just inside, you can't, but you might not realize it yet. Farther in, the tidal forces grow stronger, and at the very center lies the singularity, a point where density becomes infinite, where space-time curvature becomes infinite, where our equations break down and stop making sense. We don't know what happens at the singularity. General relativity predicts it but can't describe it. Quantum mechanics might have something to say, but we don't yet have a complete theory of quantum gravity. The singularity is a place where our understanding ends. Black holes aren't cosmic vacuum cleaners, though. They don't suck things in from vast distances. From far away, a black hole's gravity is just like any other object's gravity. If the sun suddenly became a black hole, don't worry, it won't. Earth would continue orbiting normally. We'd freeze without sunlight, but we wouldn't be pulled in. Black holes are strange, yes, but they're also just gravity taken to its logical extreme. Curvature so steep that it closes off a region of space-time from the rest of the universe. a place where all roads lead inward and the way out is forbidden by the structure of reality itself. The gravitational pull at the surface of Jupiter is only about 2.5 times stronger than Earth's, despite Jupiter being 318 times more massive. Jupiter is enormous. It contains more mass than all the other planets in the solar system combined. Thus, you could fit more than 1,300 Earths inside its volume. And yet, if you could somehow stand on Jupiter's surface, the outer edge of its thick atmosphere, you'd weigh only about 2.5 times what you weigh on Earth. Why isn't Jupiter's surface gravity much stronger? Because gravity weakens with distance, and Jupiter is so large that its surface is very far from most of its mass. Imagine Jupiter's mass concentrated at its centre. The surface is about 70,000 kilometers from that centre, much farther than Earth's surface is from Earth's centre, about 6,400 kilometers. Yes, Jupiter has more mass, but you're also standing farther away from it. The two effects partially cancel each other out. In fact, if you could somehow compress Jupiter without changing its mass, squeeze it down to Earth's size, the surface gravity would be crushing. About 80 times Earth's gravity, but spread that mass out into a giant sphere, and the surface gravity becomes much more moderate. This is true for all planets and stars. Surface gravity depends on both mass and radius. A small dense object can have stronger surface gravity than a large diffuse one, even if the large one is more massive overall. It's a reminder that gravity is about proximity as much as mass. Distance matters. Geometry matters. The universe is full of trade-offs, balances, equations where multiple factors compete and compromise. Even something as straightforward as gravity has subtleties that resist simple intuition. Gravity bends light, allowing massive objects to act as cosmic magnifying glasses through gravitational lensing. Light has no mass, and for a long time people wondered whether gravity could affect it. Well, Newton's theory suggested it shouldn't. But Einstein's general relativity made a clear prediction. Light follows the curvature of space-time, and since mass curves space-time, light should bend near massive objects. The first test came in 1919 during a solar eclipse. Astronomers measured the positions of stars near the sun's edge. According to general relativity, the sun's mass should bend the starlight passing nearby, making the stars appear slightly displaced from their true positions. The observations matched Einstein's predictions. Gravity bends light. This bending is called gravitational lensing, and it's become one of the most powerful tools in astronomy. When light from a distant galaxy passes near a massive object, like a closer galaxy or a cluster of galaxies, the light bends around it. Sometimes the background galaxy appears distorted, stretched into arcs or rings. Sometimes it appears in multiple places at once, as light takes different curved paths around the foreground object. In some cases, gravitational lensing magnifies the background galaxy, allowing us to see objects that would otherwise be too faint and distant to detect. Galaxy clusters act like natural telescopes, bending and amplifying the light from the early universe. We've even used gravitational lensing to map dark matter. Dark matter doesn't emit light, but it has mass, so it curves space-time. By observing how light bends around galaxy clusters, we can infer where the dark matter is. creating maps of invisible mass revealed only through its gravitational fingerprint. Light and gravity intertwined, the shape of space guiding the path of photons. It's elegant, really. Gravity doesn't just pull on matter, it shapes the very light by which we see. The concept of gravitational redshift means light climbing out of a gravitational field loses energy and shifts toward red wavelengths. Photons, particles of light, don't have mass, but they do have energy. And according to general relativity, they're affected by gravity in a subtle but measurable way. When a photon climbs out of a gravitational well, say, escaping from the surface of a star, it has to work against gravity, not in the Newtonian sense of lifting mass, but by expending energy to climb through curved space-time. As it escapes, the photon loses energy. What does it mean for a photon to lose energy? It can't slow down. All photons travel at the speed of light. Instead, the photon's wavelength increases. Its frequency decreases. It shifts toward the red end of the spectrum. This is gravitational redshift. The effect is tiny for Earth. Light leaving Earth's surface and reaching a satellite in orbit is redshifted by about 1 part in a billion. But near more extreme objects, the effect becomes dramatic. Light escaping from the surface of a white dwarf is noticeably redder than when it was emitted. Near a neutron star, the redshift is even more pronounced. And near the event horizon of a black hole, light is redshifted so severely that photons lose nearly all their energy before escaping, if they escape at all. Gravitational redshift is one of the clearest demonstrations that gravity affects time as well as space. The photon's frequency is essentially a clock, and that clock runs slower in stronger gravity. The redshift is time dilation. Translated into the language of light, every photon that reaches your eyes from the sun or stars has been gravitationally redshifted ever so slightly as it climbed out of those gravitational wells. The universe is full of these subtle shifts, tiny distortions in the light we see, written into the spectrum by gravity's influence. Freefall is the most natural state of motion. It's what you do when only gravity acts on you. We think of falling as violent, uncontrolled, but in physics, free fall is actually the purest, most natural state of motion. It's what happens when you move through space-time unimpeded, following the straightest possible path through curved space. When you stand on the ground, you're not in free fall. The ground pushes up on your feet, preventing you from following your natural trajectory through space-time. You feel weight because you're being accelerated upward, constantly, by the electromagnetic forces between atoms in the ground and atoms in your feet. You're being held back from falling, but let go, jump off a diving board, step out of an airplane, and suddenly you're in free fall. And here's the strange part, you feel weightless. There's no sensation of gravity pulling you down. You simply float, at least from your own perspective, because you're following space-time's natural curvature. Astronauts in orbit are in continuous free fall. They're falling toward Earth, but moving sideways fast enough that they keep missing it. From their perspective, they're weightless, floating freely. They're not fighting gravity. They're surrendering to it completely, and in that surrender they find weightlessness. Einstein called this the happiest thought of his life. The realization that someone in free fall doesn't feel their own weight. It's the equivalence principle. Locally, you can't tell the difference between floating in deep space and falling freely in a gravitational field. Both feel the same, both are natural. Maybe there's a lesson in that. Fighting gravity, standing, resisting, holding yourself up, requires constant effort. But let go, fall freely, and there's a kind of peace in it. Not the violence of crashing, but the serenity of surrendering to the shape of space-time, moving as the universe guides you. The equivalence principle states that you can't tell the difference between standing in gravity and accelerating in a rocket. Imagine you're in a windowless room. You feel weight pressing down on your feet. Are you standing on Earth's surface, or are you inside a rocket accelerating through deep space at 9.8 meters per second squared? According to the equivalence principle, there's no experiment you can perform inside that room to tell the difference. Gravity and acceleration are locally indistinguishable. Drop a ball and it falls to the floor, but is it falling because gravity pulls it down, or because the floor is accelerating upward to meet it? Both descriptions are equally valid. Shine a laser across the room, and it appears to bend downward. But is space-time curved by gravity, or is the room accelerating upward while the light travels straight? Again, both descriptions work. This simple observation was Einstein's key insight, the seed from which general relativity grew. If gravity and acceleration are equivalent, and then gravity must affect not just matter but also light, time, and the structure of space-time itself. The equivalence principle is local though. It applies in a small enough region that tidal effects, differences in gravitational strength across distance, are negligible. In a large enough room, or over a long enough time, you could detect tidal forces and distinguish true gravity from acceleration. But locally, in a small region, they're the same. It's a profound statement about the nature of reality. What you experience as gravity isn't a force pulling you down. It's the feeling of being prevented from moving freely through curved space-time. Standing on the ground is, in a sense, like being continuously accelerated upward by the planet beneath your feet. Gravity wells are often visualized as depressions in a rubber sheet, but this analogy actually uses gravity to explain gravity. You've probably seen the image, a rubber sheet stretched flat with a bowling ball placed in the middle, creating a depression. Marbles rolled near the depression curve toward the bowling ball, illustrating how mass curves space-time and affects nearby objects. It's a useful analogy. It helps visualize curvature in a way our three-dimensional minds can grasp, but it has a subtle problem. It uses gravity to explain gravity. Why does the bowling ball create a depression in the sheet? Because Earth's gravity pulls it down, stretching the rubber. Why do the marbles roll toward the bowling ball? Because gravity pulls them into the depression. The entire analogy depends on gravity, the very thing we're trying to explain. The real curvature of space-time isn't like a dip in a sheet. It's curvature in four-dimensional space-time, a mathematical warping of the geometry itself, not embedded in any higher dimensional space with its own gravity. It's intrinsic curvature, not extrinsic. Our brains didn't evolve to visualize four-dimensional geometry. We think in three spatial dimensions plus time as a separate thing. Space-time curvature is genuinely difficult to picture accurately. The rubber sheet helps, but it's a limited metaphor, a shadow of the real thing. Perhaps that's okay. Some aspects of the universe resist visualization. We can describe them mathematically, predict them, measure them, confirm them with experiments. But truly seeing them in the way we see a tree or a river may be beyond us. We're left with analogies, approximations, mathematical truths that we understand intellectually but can't quite picture. And maybe that's part of the wonder. The universe is stranger than our intuitions, deeper than our visualizations. Gravity curves space-time in ways we can calculate but not fully envision, and we move through that invisible geometry every moment of our lives. Tidal forces are caused by the difference in gravitational pull across an object's size. Gravity doesn't pull evenly on extended objects. The side of an object closer to a massive body feels stronger gravity than the far side. This difference in gravitational strength across the object's size is called a tidal force. For small objects near weak gravitational fields, tidal forces are negligible. You don't notice them sitting at your desk, but they're always there, subtly stretching you in one direction and compressing you in another. The moon creates tidal forces on Earth, stretching the planet slightly along the Earth-Moon axis and compressing it perpendicular to that axis. The solid Earth deforms only slightly, but the oceans, being fluid, respond more dramatically, creating the tides. Near more extreme gravitational fields, tidal forces become violent. Approach a black hole, and the tidal forces grow rapidly. Your feet, being closer to the black hole than your head, experience stronger gravity. The difference in pull stretches you. This process is called spaghettification, a whimsical name for a rather unpleasant fate. For a stellar mass black hole, you'd be spaghettified long before reaching the event horizon. The tidal forces would stretch you thinner and thinner, ripping atoms apart, until you were a stream of particles falling inward. Interestingly, for supermassive black holes, millions or billions of times the Sun's mass, the event horizon is so far from the singularity that tidal forces at the horizon are relatively mild. You could, theoretically, pass through the event horizon of a supermassive black hole and survive for a while, at least until you got closer to the singularity. Tidal forces remind us that gravity isn't uniform. It varies with distance, and that variation has consequences, gentle ones, like ocean tides, and extreme ones, like the destruction of anything that ventures too close to a black hole's singularity. The Cavendish experiment in 1798 was the first to measure the gravitational constant g, determining the actual strength of gravity. Newton described how gravity behaves. He gave us the inverse square law, the equations to predict planetary orbits, the mathematical framework. But there was a missing piece: the gravitational constant, g, the number that determines gravity's actual strength. Newton's equations contained g, but he never measured it. He didn't know Earth's mass or the Sun's mass in absolute terms. He knew their ratios, their relative influences, but not the fundamental strength of gravity itself. That changed in 1798, when Henry Cavendish performed one of the most delicate experiments in the history of physics. He suspended a lightweight rod with two small lead spheres on opposite ends, hanging from a thin wire. Then he brought two larger lead spheres near the smaller ones. The gravitational attraction between the spheres was tiny, far weaker than the breeze from a breath, but Cavendish's apparatus was sensitive enough to detect it. The rod twisted slightly, and by measuring that twist, Cavendish could calculate the gravitational force. From that he derived G. The value he obtained was remarkably accurate. Modern measurements give G as approximately 6.674 times 10 to the minus 11 cubic meters per kilogram per second squared. Cavendish's result was within about 1% of this value. Interestingly, G is one of the least precisely known fundamental constants. Measuring gravity is hard because it's so weak. Electromagnetic forces overwhelm it at small scales. Modern experiments still struggle to pin down G's value with the precision we have for other constants, like the speed of a light or Planck's constant. But Cavendish did it. He weighed the Earth, in a sense, by measuring the gravitational attraction between lead spheres in a lab. It's a testament to how carefully designed experiments can reveal the universe's deepest secrets. Dark matter was discovered because galaxies rotate too fast. There's not enough visible matter to provide the gravity holding them together. In the 1970s, astronomer Vera Rubin studied the rotation of spiral galaxies. She measured how fast stars orbit around galactic centers at various distances. According to Newton's laws, and Einstein's for that matter, stars farther from the center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner ones. But that's not what Rubin found. Stars at the edges of galaxies were moving just as fast, sometimes faster, than stars closer to the center. The rotation curves were flat, not declining. This was a problem. For the outer stars to move that fast, there had to be far more mass in the galaxy than we could see. The visible stars, gas and dust weren't nearly enough. Either our understanding of gravity was wrong, or there was something else, something invisible, providing the extra gravitational pull. We call it dark matter. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all as far as we can tell. It interacts primarily through gravity, and there's a lot of it, about 5 times as much dark matter as ordinary matter in the universe. We've confirmed its existence through multiple lines of evidence. Gravitational lensing shows that massive invisible structures bend light. The cosmic microwave background contains patterns that only make sense if dark matter exists. Galaxy cluster dynamics require it. But we still don't know what dark matter is. It's not made of atoms. It's not any particle in the standard model of physics. It's something new, something we've only detected through its gravitational effects. About 85% of the matter in the universe is invisible to us, revealed only by the way it pulls on the things we can see. It's humbling. We've mapped the visible universe, catalogued billions of galaxies, and yet most of the matter is hidden, dark, unknown. Gravity reveals its presence, but the mystery of its nature remains. Gravitational potential energy is why water flows downhill, and why you have to work to climb stairs. Energy comes in many forms, and one of the most familiar is gravitational potential energy. The energy stored in an object's position within a gravitational field. Lift a book off the floor and place it on a shelf. You've done work against gravity, and that work is now stored as potential energy. The book sitting on the shelf has more potential energy than it did on the floor. If it falls, that potential energy converts into kinetic energy, the energy of motion. This is why water flows downhill. Water in a mountain lake has high gravitational potential energy. As it flows downward through rivers and streams, that potential energy decreases, and the lost potential energy becomes kinetic energy, the water's motion, and heat from friction. This is also why climbing stairs is tiring. You're lifting your entire body mass against gravity, increasing your potential energy with every step. The chemical energy from the food you ate is being converted into gravitational potential energy. When you walk back down, that potential energy decreases. Though your muscles still have to work to control your descent, gravitational potential energy is relative, not absolute. There's no 0 point. We can only measure differences in potential energy, how much energy it takes to move something from one position to another. In a sense, what matters isn't where you are, but where you are relative to where you could be. Rivers flow, rain falls, objects tumble downward, all because nature favors lower gravitational potential energy. It's entropy at work, systems seeking their most probable states. And in a gravitational field, lower is more probable, more stable, more at rest. The term zero gravity is actually a misnomer. Gravity exists everywhere in the universe. We often talk about astronauts experiencing zero gravity in space, but the term is misleading. Gravity is everywhere. It's a property of space-time, extending infinitely in all directions, weakening with distance but never truly vanishing. The International Space Station orbits about 400 kilometers above Earth's surface. At that altitude, Earth's gravity is still about 90% as strong as it is on the ground. The astronauts aren't beyond gravity's reach, far from it. They're held in orbit by gravity. What we call zero gravity is really microgravity, a state where gravitational effects are very small but not absent. The astronauts are in free fall, continuously falling around Earth, and that free fall creates the sensation of weightlessness. Even in deep space, far from any star or planet, gravity exists. Every particle in the universe pulls on every other particle. The pulls are unimaginably faint, but they're there. You could be billions of light years from the nearest galaxy, and you'd still feel a tiny gravitational tug from every mass in the observable universe. Gravity has no off switch. There's no shielding, no way to block it. Every form of mass and energy contributes to space-time curvature. Even in the emptiest regions of space, quantum fluctuations create temporary gravitational effects. The universe is a web of gravitational influences, everything connected to everything else through the curvature of space-time. You're never truly isolated from gravity. You're always part of the cosmic gravitational field, responding to the combined influence of all the mass and energy around you, near and far. Gravity causes orbits to precess. Mercury's orbit slowly rotates in a way Newton's laws couldn't fully explain. Most orbits aren't perfect ellipses, or they're close, but subtle effects cause them to shift over time. One such effect is called precession, the slow rotation of an orbit's orientation in space. Mercury's orbit precesses noticeably. Each time Mercury completes one orbit around the Sun, the point of closest approach, perihelion, shifts slightly. Over a century, Mercury's perihelion precesses by about 574 arc-seconds, about 1/6 of a degree. Most of this precession can be explained by the gravitational influences of other planets, Venus, Earth, Jupiter pulling on Mercury as they orbit. Newton's laws account for about 531 arcseconds per century, but that leaves 43 arcseconds unaccounted for. It's a small discrepancy, but it's real, measurable, and persistent. 19th century astronomers noticed it and couldn't explain it. Thus some proposed an undiscovered planet closer to the Sun, which they named Vulcan. They searched for it. It wasn't there. Then Einstein published General Relativity in 1915, and the mystery was solved. General Relativity predicts that orbits in curved space-time should precess slightly more than Newton's laws suggest. When Einstein calculated Mercury's precession using his new equations, the extra 43 arcseconds appeared naturally. No new planet, no modification to gravity, just a more accurate description of space-time curvature. It was one of the first confirmations of general relativity, and it was profoundly satisfying. A century-old puzzle, solved not by discovering new objects but by understanding gravity more deeply. Precession is subtle, but it's real. Even the orbits of planets aren't static. They shift slowly, responding to the complex gravitational dance of the solar system and the curvature of space-time itself. The Hill sphere defines the region where an object's gravity dominates over other nearby massive bodies. Every object with mass creates a gravitational field, but in a system with multiple masses, like a planet orbiting a star, there's a question. Where does one object's gravitational influence end and another's begin? The Hill sphere is the answer. It's the region around an object where that object's gravity dominates over the tidal forces from a more massive nearby body. Inside the Hill sphere, smaller objects can orbit stably. Outside it, they're more influenced by the larger body and will eventually be pulled away. Earth's Hill sphere extends about 1.5 million kilometers from the planet. The Moon, at an average distance of about 384,000 kilometers, orbits comfortably within this sphere. Earth's gravity holds the Moon more strongly than the Sun's gravity does, even though the Sun's gravitational pull on the Moon is actually stronger in absolute terms. Wait, how can Earth hold the Moon if the Sun pulls on it more strongly? Because what matters isn't the absolute gravitational force, but the gradient, the difference in force between one side of the orbit and the other. Earth's gravity varies more steeply over the Moon's orbital distance than the Sun's does, and that difference is what defines the Hill sphere. Satellites and space stations orbit within Earth's Hill sphere. Spacecraft travelling to other planets must leave Earth's Hill sphere to enter the Sun's gravitational domain. It's a transition, a crossing of boundaries in the invisible landscape of gravitational influence. The Hill sphere isn't a rigid boundary. Objects just outside it can persist for a while before drifting away. But over long timescales, it defines the region of gravitational dominance, the space where an object can truly call the orbits its own. Lagrange points are special locations where the gravity of two large objects creates stable or semi-stable positions for smaller objects. In the gravitational dance between two massive bodies, say the Earth and the Sun, there are 5 special points where a small object can sit and maintain its position relative to both bodies. These are called Lagrange points, named after mathematician Joseph Louis Lagrange, who discovered them in the 18th century. At these points, The gravitational pulls of the two large bodies, and combined with the centrifugal effect of orbiting, balance perfectly. A spacecraft placed at a Lagrange point doesn't need to fire its engines constantly to stay there, at least not much. 3 of these points, L1, L2 and L3, lie along the line connecting the two massive bodies. They're unstable. A spacecraft will drift away if not corrected, but they're still useful. L1, between Earth and Sun, is where solar observatories sit, always watching the Sun. L2, on the opposite side of Earth from the Sun, is where the James Webb Space Telescope orbits, about 1 million miles away, shielded from the Sun's heat and light. The other 2 points, L4 and L5, lie 60 degrees ahead and behind the smaller body in its orbit. These are stable. Objects placed there tend to stay there, pulled back if they drift. Jupiter has accumulated swarms of asteroids at its L4 and L5 points, thousands of them, called Trojan asteroids, trapped in these gravitational sweet spots. Lagrange points are solutions to a complex mathematical problem, places where the equations balance in just the right way. They're invisible, intangible. There's nothing physically there. But they're real, defined by the geometry of gravitational fields, and we've learned to use them, parking our telescopes and observatories in these quiet corners of the gravitational landscape. Gravitational binding energy is the energy it would take to completely disassemble an object against its own gravity. Every object held together by gravity contains energy, potential energy, stored in the gravitational field itself. Disassembling that object, pulling every piece of it infinitely far away from every other piece, would require energy. That's the gravitational binding energy. For small objects, the binding energy is negligible. For planets and stars, it's enormous. Earth's gravitational binding energy is about 2 times 10 to the 32nd power joules. That's the energy it would take to completely disassemble the planet, scattering every atom into space. It's roughly the total energy output of the Sun over an entire week. The Sun's binding energy is far greater, about 4 times 10 to the 48th power joules. To put that in perspective, it exceeds the total energy the Sun will radiate over its entire 10 billion year lifetime. The Sun is so tightly bound by its own gravity that even burning for billions of years doesn't release as much energy as would be needed to take it apart. This is why gravitational collapse releases so much energy. When a cloud of gas collapses to form a star, gravitational potential energy converts into heat. Half of it heats the gas and half radiates away. The energy released during the Sun's formation was enormous, heating the protostar until nuclear fusion ignited. Gravitational binding energy is also why supernovae are so violent. When a massive star's core collapses into a neutron star or black hole, the gravitational binding energy released, in just seconds, can outshine an entire galaxy. Gravity holds things together, and holding them together stores energy. Break those bonds, and the energy is released. Or reverse it. Bring scattered matter together, and energy floods the system, lighting up the cosmos. Supermassive black holes at galactic centers can have masses billions of times that of our Sun. At the heart of most galaxies, including our own Milky Way, lies a supermassive black hole. These aren't the remnants of collapsed stars. They're far larger, with masses ranging from millions to tens of billions of times the Sun's mass. The black hole at the centre of the Milky Way, called Sagittarius A star, pronounced A star, has a mass of about 4 million suns. We know this because we've watched stars orbit around it, tracing elliptical paths over years and decades. By measuring their speeds and orbital periods, we can calculate the mass of the invisible object they're orbiting. Some supermassive black holes are far larger. The black hole at the centre of the galaxy M87 has a mass of about 6.5 billion suns. It's the black hole we imaged in 2019, the first direct image of a black hole's shadow, a dark circle surrounded by glowing matter. Despite their enormous masses, supermassive black holes aren't particularly dense, at least not in the sense of how tightly packed they are overall. The event horizon of a billion solar mass black hole extends for billions of kilometers, roughly the size of our solar system. The average density within that volume is surprisingly low, less than water. But don't be fooled. The singularity at the center, if it exists as general relativity predicts, is infinitely dense. The low average density just means there's a lot of empty space between the event horizon and the center. We still don't fully understand how supermassive black holes form. Did they grow gradually, accreting matter over billions of years? Or did they form from massive seed black holes in the early universe? The answer is probably both, and the details are still being worked out. What's clear is that supermassive black holes shape galaxies. Their gravity influences the orbits of billions of stars. The energy released as matter falls into them drives powerful jets and winds that regulate star formation across the galaxy. They're not just inhabitants of galaxies, they're architects. Frame dragging is the twisting of space-time caused by rotating massive objects. Space-time doesn't just curve, it can also twist. When a massive object rotates, it drags space-time along with it, like honey swirling around a spinning spoon. This is called frame dragging, or the Lense-Thirring effect, after the physicists who first predicted it in 1918. The effect is subtle near Earth. As our planet rotates, it twists the space-time around it ever so slightly. Satellites in polar orbits experience a tiny drift in their orbital planes, about 2 meters per year, due to Earth's frame dragging. It took decades to measure this effect. In 2004, NASA launched Gravity Probe B, a satellite carrying 4 ultra-precise gyroscopes. Over a year and a half, the gyroscope's axis drifted by about 37 milliseconds, roughly the width of a human hair seen from 10 miles away. It matched the prediction from general relativity almost perfectly. Near more extreme objects, frame dragging becomes dramatic. Around a rotating black hole, space-time is dragged so forcefully that nothing can remain stationary. Close to the event horizon lies a region called the ergosphere, where the twisting of space-time is so intense that you'd have to move faster than the speed of light to stay in the same place. Since that's impossible, everything, including light, is forced to rotate along with the black hole. This creates strange possibilities. Theoretically, you could extract energy from a rotating black hole by dropping something into the ergosphere in just the right way. It's called the Penrose process, and it's one of the few ways to extract energy from a black hole. Frame dragging is space-time in motion, rotating, twisting, carrying everything along with it. It's yet another way that gravity is more than just attraction. It's the dynamic, flowing geometry of reality itself. The gravitational two-body problem has an exact mathematical solution, but add a third body and it becomes unsolvable in general. When Newton formulated his laws of motion and gravity, he could solve the two-body problem exactly. Give him two objects, say, the Earth and the Moon, and he could predict their orbits perfectly for all time. The mathematics works out cleanly. The orbits are ellipses, and the equations tell you exactly where each object will be at any future moment. But add a third body, and everything changes. The three-body problem, predicting the motion of three objects under mutual gravitational attraction, has no general solution. There's no formula you can write down that gives you the positions for all time. The system is deterministic, meaning the future is in principle predictable, but it's also chaotic, meaning tiny differences in starting conditions lead to wildly different outcomes. This isn't just a mathematical curiosity. It has real consequences. The solar system contains many bodies, planets, moons, asteroids, all pulling on each other. We can predict orbits quite well using computers and numerical approximations, but over very long timescales, the predictions become uncertain. Small perturbations accumulate. Chaos creeps in. We know, for instance, that Mercury's orbit is chaotic. Given enough time, millions of years, its orbit could become unstable. It might collide with Venus or get ejected from the inner solar system. We can't predict which will happen, or when, because the system is fundamentally chaotic. There are special cases where three-body systems are stable, certain resonances, certain symmetries, but in general, three bodies make for unpredictable futures. It's humbling, really. We can describe gravity precisely, write down exact equations, and yet predicting something as simple as three objects pulling on each other defies exact solution. Chaos lurks in the equations, reminding us that understanding the rules doesn't always mean we can predict the outcome. Gravitational microlensing allows us to detect exoplanets when their gravity briefly magnifies the light from a distant star. Imagine you're looking at a distant star, and by pure chance, another star passes almost directly between you and that distant star. For a brief time, days or weeks, the foreground star's gravity acts as a lens, bending and magnifying the light from the background star. The background star brightens, then dims again as the alignment shifts. This is gravitational microlensing, and it's a powerful tool for finding planets. If the foreground star has a planet orbiting it, the planet's gravity creates its own tiny lensing effect, superimposed on the star's lensing. The background star's brightness shows a brief spike, sometimes lasting just hours, as the planet's gravity magnifies its light. The spike is small, subtle, but detectable. Microlensing is unique among planet detection methods. It doesn't require the planet to transit in front of its star or to tug its star back and forth. It works for planets far from their stars, in wide orbits where other methods struggle. It's sensitive to planets of all sizes, from gas giants to small rocky worlds. The downside is that each event is unique and unrepeatable. The alignment between distant star, foreground star and Earth happens by chance and never repeats. Once detected, the planet can't be studied further. It's too far away, too faint. We know it exists, but we'll likely never see it again. Microlensing has discovered dozens of exoplanets, many in the cold outer regions of their solar systems. It's given us a glimpse into planetary populations we couldn't study any other way. And it's a reminder that gravity reveals things in unexpected ways, magnifying light across cosmic distances, turning distant stars into temporary telescopes. The cosmic microwave background shows tiny ripples from quantum fluctuations amplified by gravity in the early universe. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that, it was a hot, opaque plasma. When atoms formed, light could finally travel freely through space. That light has been travelling ever since, stretched by the universe's expansion into microwaves. We call it the Cosmic Microwave Background, or CMB. The CMB is remarkably uniform, almost the same temperature in every direction, about 2.7 Kelvin above absolute zero, but not perfectly uniform. There are tiny fluctuations, variations of about 1 part in 100,000. These fluctuations are seeds. They're the imprints of quantum fluctuations from the very early universe, moments after the Big Bang, blown up to cosmic scales by a rapid expansion called inflation. Where the density was slightly higher, gravity pulled more matter in over time. Where it was slightly lower, less matter accumulated. Over billions of years, those tiny density differences grew into the large-scale structure we see today: galaxies, galaxy clusters, vast cosmic voids. Gravity took the quantum noise of the early universe and sculpted it into everything. We've mapped the CMB with extraordinary precision, and satellites like WMAP and Planck have measured the temperature variations across the entire sky, creating detailed maps of the infant universe. These maps tell us the universe's age, its composition, its geometry. They reveal that the universe is flat, that dark matter exists, that dark energy drives accelerated expansion. All of this from tiny ripples in ancient light, amplified by gravity over cosmic time. The CMB is a snapshot of the universe when it was 380,000 years old, and written into that snapshot are the origins of everything we see around us today. Gravitational collapse is inevitable for any sufficiently massive object that exhausts its internal pressure sources. Stars spend their entire lives in a balance between two forces. Gravity pulls inward, trying to collapse the star. Pressure from heat and nuclear fusion pushes outward, resisting that collapse. As long as the star has fuel to burn, the balance holds, but eventually the fuel runs out. For stars like the Sun, the end is gentle. When hydrogen fusion stops, the core contracts and heats until helium begins fusing. Eventually even that stops, and the outer layers drift away, leaving behind a white dwarf, a dense ember of carbon and oxygen, supported not by fusion but by electron degeneracy pressure, a quantum effect that prevents electrons from being squeezed too closely together. For more massive stars, the end is more dramatic. They fuse heavier and heavier elements, helium, carbon, oxygen, silicon, until they produce iron. Iron won't fuse and release energy. The fusion stops. The core, no longer supported, collapses in less than a second. The collapse is catastrophic. The outer layers fall inward, then rebound off the incredibly dense core, creating a supernova, an explosion so bright it can outshine a galaxy. What's left behind is either a neutron star supported by neutron degeneracy pressure, or, if the star is massive enough, a black hole. there's a limit to how much pressure can resist gravity. Electron degeneracy pressure has a limit, the Chandrasekhar limit, about 1.4 solar masses for a white dwarf. Neutron degeneracy pressure has a limit too, around 2 to 3 solar masses for a neutron star. Beyond that, nothing can stop the collapse. Gravity wins completely and the result is a black hole. Stars fight gravity for billions of years, but gravity is patient. In the end, gravity always wins. And the Schwarzschild radius defines how small a mass must be compressed to become a black hole. Every mass has a Schwarzschild radius, the size it would need to be compressed to in order to become a black hole. It's not a property of black holes specifically, it's a property of mass itself, a threshold written into the structure of space-time. For Earth, the Schwarzschild radius is about 9 millimeters, the size of a marble. Compress the entire planet down to that size, and it would become a black hole. Of course, we can't do that. Earth doesn't have enough mass to collapse on its own, and we don't have the technology to compress it artificially. For the Sun, the Schwarzschild radius is about 3 kilometers. The Sun would need to fit inside a sphere 6 kilometers across to become a black hole. Again, impossible. The Sun doesn't have the mass to collapse that far, even after it exhausts its fuel. But for more massive stars, gravitational collapse can reach the Schwarzschild radius naturally. When the core of a sufficiently massive star collapses, nothing can stop it. It crosses its Schwarzschild radius, and an event horizon forms. A black hole is born. The Schwarzschild radius scales linearly with mass. Double the mass and the radius doubles. A black hole with 1 billion solar masses has a Schwarzschild radius of about 3 billion kilometers, roughly 20 times the distance from the Sun to Earth. Interestingly, this means more massive black holes are less dense on average. A supermassive black hole's event horizon might have an average density less than water, even though its singularity, if it exists, is infinitely dense. The Schwarzschild radius is a boundary in space-time, the point of no return. It's different for every mass, but the principle is the same. Compress anything small enough, and gravity closes off a region of space from the rest of the universe. Gravitational potential creates a universal ranking. Everything naturally wants to move to lower gravitational potential. In physics, we often talk about potential energy, but there's a related concept called gravitational potential. Essentially, the potential energy per unit mass. It's a way of describing the gravitational landscape, assigning a value to every point in space that tells you how deep you are in a gravitational well. Things naturally move from higher potential to lower potential. Water flows downhill because downhill is lower potential. Your satellites slowly spiral inward due to drag because lower orbits have lower potential. Matter falls into black holes because the potential keeps dropping all the way to the singularity. This is a general principle in physics. Systems tend toward lower energy states. A ball rolls downhill, heat flows from hot to cold, and in gravitational fields matter drifts toward lower potential. But there's a subtlety. Moving to lower potential releases energy. That energy has to go somewhere. Often, it becomes kinetic energy, motion, or heat, friction. A falling object speeds up, converting potential energy into kinetic energy. Water flowing downhill generates heat through friction with rocks and riverbed. In the universe at large, gravitational collapse releases enormous amounts of energy. Gas clouds collapsing to form stars heat up, eventually igniting fusion. Matter falling into black holes heats up and radiates intensely before crossing the event horizon. The brightest objects in the universe, quasars powered by supermassive black holes consuming matter, shine because gravitational potential energy is being released. Potential is a map of possibilities. It tells you where things want to go, where energy can be released, where stability lies. And in that map, lower is always more favoured, always pulling at everything. A gentle but relentless guide toward what gravity prefers. The Earth-Moon system is actually a double planet from a gravitational dynamics perspective. Most moons are small compared to their planets. Mars's moons are tiny, just captured asteroids really. Jupiter's moons, even the large ones, are dwarfed by Jupiter itself. In these systems, the planet clearly dominates, and the moon is just an orbiting satellite. But the moon is different. It's unusually large compared to Earth, about 1/81st of Earth's mass, and more than a quarter of Earth's diameter. This makes the Earth-Moon system unusual. When two bodies orbit each other, they don't actually orbit around one body's centre. They both orbit around their common centre of mass, called the barycenter. For most planet-moon systems, the barycenter is inside the planet, close to its centre, so it looks like the moon orbits the planet. For Earth and Moon, the barycenter is about 4,700 kilometers from Earth's centre, still inside Earth, but not by much. Earth is about 6,400 kilometers in radius, so the barycenter is roughly 3/4 of the way from Earth's center to its surface. Both Earth and Moon orbit this barycenter, or Earth wobbles in a small circle, while the Moon orbits in a larger circle. From a gravitational dynamics perspective, they are a binary system, two bodies orbiting their mutual center of mass. Some astronomers call the Earth-Moon system a double planet. The term isn't official, but it captures something important. The Moon isn't just a satellite, it's a partner, a companion, large enough to move Earth as much as Earth moves it. We're not just a planet with a moon, we're a pair, bound together, dancing around a shared centre of gravity, influencing each other's tides, rotation, and stability. The moon shaped Earth's history, stabilizing its tilt, creating tides that may have been crucial for early life. We're linked gravitationally and historically in ways deeper than most planets and their satellites. Yeah, modified Newtonian dynamics, MON, is an alternative to dark matter that proposes gravity behaves differently at extremely weak accelerations. Dark matter is the leading explanation for why galaxies rotate too fast, invisible matter providing extra gravity. But there's another possibility. What if gravity itself behaves differently than we think? Modified Newtonian dynamics, or MOND, proposes that at very low accelerations, far weaker than anything we experience on Earth, gravity becomes stronger than Newton's or Einstein's theories predict. Instead of falling off as the inverse square of distance, it falls off more slowly. This would explain galactic rotation curves without needing dark matter. At the edges of galaxies where accelerations are tiny, gravity would be stronger than expected, keeping stars moving fast. Desmond fits galactic rotation curves surprisingly well. It predicted, before observations confirmed, certain relationships between a galaxy's visible matter and its rotation speed. For individual galaxies, MOND works remarkably well, sometimes better than dark matter models. But MOND struggles with larger scales. Galaxy clusters, gravitational lensing, and the cosmic microwave background all point strongly toward dark matter. MOND can't explain these without additional modifications, and those modifications start to look ad hoc, tailored to fit the data rather than emerging from fundamental principles. Most physicists favour dark matter because it fits the full range of observations more naturally. But MOND remains interesting. It's a reminder that our understanding of gravity might still be incomplete, especially at the weakest accelerations where we have the least direct experimental data. Maybe gravity does something strange in those regimes, or maybe dark matter exists, and the success of MOND in certain cases is a coincidence, or a hint of deeper physics we don't yet understand. The question isn't fully settled, and that's part of what makes it interesting. The universe's expansion is accelerating, driven by something we call dark energy that acts opposite to gravity. In the 1990s, astronomers studying distant supernovae made a startling discovery. They expected the universe's expansion to be slowing down, decelerated by gravity pulling everything back together. Instead, they found the expansion was speeding up. This was shocking. Gravity attracts. It should slow expansion, not accelerate it. But the data were clear. Distant supernovae were dimmer than expected, meaning they were farther away than they should be if expansion were slowing. The universe's expansion was accelerating. We don't know what causes this acceleration. We call it dark energy, but that's just a name for our ignorance. It's not matter, it's not radiation, it's something else, something that fills all of space and pushes outward, counteracting gravity. The simplest explanation is the cosmological constant, a kind of energy inherent to space itself. Einstein introduced this concept in 1917 to keep the universe static, then abandoned it when expansion was discovered. Now it's back, but with a twist. Instead of balancing expansion, it drives it. Dark energy comprises about 68% of the universe's total energy. Dark matter is about 27%. Ordinary matter, everything we can see, all the stars and galaxies, is less than 5%. Most of the universe is invisible and poorly understood. The fate of the universe depends on dark energy. If it remains constant, the universe will expand forever, accelerating, growing colder and emptier. Galaxies will drift apart. Eventually, stars will burn out, and the cosmos will fade into darkness. If dark energy changes over time, the future could be different, perhaps even a reversal, a big crunch. We're living in a universe dominated by something we don't understand, something that pulls space-time apart, something that acts opposite to gravity. It's humbling. The universe is stranger than we imagined. Gravitational decoherence may explain why quantum superpositions collapse into definite states at large scales. In quantum mechanics, particles can exist in superpositions, simultaneously in multiple states until measured. An electron can be in multiple places at once. A photon can take multiple paths. But macroscopic objects, cats, people, planets, don't exhibit this behavior. They're always in definite states. Why? This is the measurement problem, one of the deepest puzzles in physics. How and why do quantum superpositions collapse into classical definiteness? One proposed answer is gravitational decoherence. The idea is that gravity, because it couples to energy and mass, fundamentally can't support superpositions of different mass distributions. When an object is in two places at once, space-time would need to be curved in two incompatible ways simultaneously. Gravity may prevent this, forcing a choice, collapsing the superposition. This is speculative, but it's testable in principle. Experiments are underway to create quantum superpositions of larger and larger objects, molecules, nanoparticles, maybe someday visible objects, and see if gravity limits how long superpositions last. If gravity causes decoherence, it would mean gravity is fundamentally different from other forces. It wouldn't be fully quantum mechanical. This could be a clue to quantum gravity, the elusive theory that unifies general relativity and quantum mechanics. It's a beautiful idea. Gravity is the bridge between quantum and classical, the force that makes the microscopic weirdness of quantum mechanics give way to the definite, tangible reality we experience. The universe's largest scale force might be what keeps the universe's smallest scale strangeness from spilling into our everyday world. Maybe. Or maybe decoherence comes from interactions with the environment and gravity has nothing to do with it. We don't know yet. But the question sits at the intersection of our two greatest theories, and the answer, when it comes, will reshape our understanding of reality. The Pioneer anomaly was an unexplained deceleration of spacecraft that challenged our understanding of gravity for decades. In the 1980s and 90s, scientists tracking the Pioneer 10 and 11 spacecraft noticed something odd. Both probes, launched in the early 1970s to explore the outer solar system, were slowing down slightly more than expected. The deceleration was tiny, about 8.74 times 10 to the power of minus 10 meters per second squared. But it was real, measurable, and consistent. For decades, the cause remained mysterious. The spacecraft were far from the sun, beyond the main planets, near where gravitational influences were weak and well understood. Yet something was slowing them down. Some wondered if it was new physics. Perhaps gravity behaves differently at vast distances, or some unknown force operates at the edge of the solar system. Others suspected it was mundane, something about the spacecraft themselves, but nobody could identify what. The mystery persisted until the 2000s, when researchers painstakingly analysed the spacecraft's thermal emissions. The Pioneers carried radioactive power sources that generated heat. Some of that heat radiated preferentially in certain directions, creating a tiny asymmetric pressure, essentially a weak rocket thrust pushing backward. When they calculated this thermal recoil force precisely, accounting for every heat source and surface on the spacecraft, the numbers matched the anomalous deceleration almost perfectly. No new physics, just subtle engineering effects that took decades to fully understand. It's a reminder that extraordinary claims require extraordinary evidence, but also that ordinary explanations can be extraordinarily difficult to pin down. The Pioneer anomaly wasn't gravity misbehaving. It was photons carrying momentum, pushing gently on aluminum and electronics, a whisper of force that accumulated over billions of miles. Sometimes the universe's mysteries resolve not into revolutionary new physics, but into the patient, careful accounting of things we already knew were true. Orbital resonances occur when gravitational interactions between orbiting bodies create stable, repeating patterns. When two bodies orbit a common center, their gravitational influences can lock into resonances, integer ratios between their orbital periods. These aren't accidents. They're stable configurations that gravitational interactions naturally create and maintain. Jupiter's moons, Io, Europa and Ganymede, are locked in a 1 to 2 to 4 resonance. For every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This isn't coincidence. Gravitational interactions between the moons nudged them into this pattern over millions of years, and the resonance is stable. Any deviation gets corrected by the same gravitational tugs. Resonances appear throughout the solar system. Neptune and Pluto are in a 2 to 3 resonance. Many asteroids orbit in resonances with Jupiter. Saturn's rings contain gaps, Cassini division, Encke gap, cleared by resonances with Saturn's moons. But resonances can also be destructive. Some orbital ratios are unstable. The Kirkwood gaps in the asteroid belt are regions where asteroids would orbit in resonance with Jupiter, but those resonances are destabilizing. Over time, gravitational perturbations eject asteroids from those orbits, leaving the gaps we observe. Resonances are gravitational music, harmonic relationships written into the orbits of bodies as they pull on each other over eons. The solar system isn't random chaos. It's patterned, structured, full of mathematical relationships that emerge naturally from gravity's influence. There's something almost musical about it. Celestial mechanics as cosmic harmony, bodies moving in ratios that would please Pythagoras. The universe composes symphonies in gravitational forces, and we're learning to hear them. The gravitational slingshots can actually slow spacecraft down as well as speed them up, depending on the approach angle. We've talked about gravity assists accelerating spacecraft, but they can also decelerate them. It all depends on the geometry, how you approach the planet and which direction you fly away. If you approach a planet from behind, relative to its orbital motion, and curve around the front, you steal some of the planet's momentum. You speed up. The planet slows down infinitesimally. This is the standard gravity assist. But if you approach from the front and curve around the back, the opposite happens. The planet steals your momentum. You slow down. The planet speeds up infinitesimally. This is useful too. Spacecraft headed toward the inner solar system, toward the sun, sometimes need to slow down. And a reverse gravity assist can do that without burning fuel. The Messenger spacecraft, which orbited Mercury, used multiple gravity assists from Earth, Venus and Mercury itself to gradually shed speed and drop into Mercury's orbit. It couldn't have gotten there otherwise. There's no fuel-efficient way to slow down that much using rockets alone. From the planet's reference frame, the spacecraft enters one speed and leaves at the same speed, just in a different direction. But from the sun's reference frame, from the larger cosmic stage, momentum is exchanged. The spacecraft's orbital energy changes, increasing or decreasing depending on the encounter geometry. It's all perfectly Newtonian. Momentum is conserved, energy is conserved. But by carefully choreographing encounters with planets, we can navigate the solar system with remarkable efficiency. borrowing and returning momentum, surfing the gravitational currents like sailors reading the wind. The Roche limit is the distance within which tidal forces will tear apart a satellite orbiting a larger body. Bring a moon too close to its planet, and tidal forces will destroy it. This threshold distance is called the Roche limit, named after French astronomer Édouard Roche, who calculated it in the 19th century. Tidal forces arise because gravity is stronger on the near side of the moon than the far side. Normally, the moon's own gravity holds it together against these tidal forces, but get close enough to the planet, and the tidal forces exceed the moon's self-gravity. The moon gets stretched, deformed, and eventually ripped apart. The exact distance depends on the densities of both bodies, and whether the satellite is held together by its own gravity or by material strength. For a fluid body held together purely by gravity, the Roche limit is about 2.5 times the planet's radius. Saturn's rings exist because of the Roche limit. Any moon that wanders inside Saturn's Roche limit, or forms there, will be torn apart. The rings are made of countless fragments, ice and rock, none larger than a house, all orbiting within the Roche limit where they can't coalesce into a moon. Some moons orbit just outside the Roche limit, stressed by tidal forces, constantly deformed. Phobos, Mars's larger moon, is gradually spiraling inward due to tidal interactions. In a few tens of millions of years, it will cross Mars's Roche limit and disintegrate, giving Mars a ring system. Since the Roche limit is a boundary between wholeness and disintegration, a distance where the gravitational gradient overwhelms structural integrity. Cross it, and gravity doesn't just pull, it tears. General relativity predicts that rotating black holes can have not one but two event horizons. For non-rotating black holes, Schwarzschild black holes, there's a single event horizon, a clean boundary beyond which nothing escapes. But add rotation, and the geometry becomes more complex. Rotating black holes, Kerr black holes, named after physicist Roy Kerr, who found the solution in 1963, have two event horizons, an outer and an inner. Between them lies a region with strange properties. Outside the outer horizon, you can still escape if you have a powerful enough rocket. Cross the outer horizon and you're trapped. But there's still structure. A region called the ergosphere where space-time is dragged around so violently that you can't stay still, but you can still, in principle, escape if you're in the right part of it. Cross the inner horizon and things get even stranger. Our equation suggests the inner horizon is unstable, perhaps singular, a place where space-time curvature becomes infinite. But we don't really know. These are regions where general relativity makes predictions, but quantum mechanics might intervene. We don't have a theory of quantum gravity to tell us what actually happens, and at the very centre, the singularity of a rotating black hole isn't a point, it's a ring, a circle of zero size but infinite density. At least that's what the mathematics suggests. Whether such a thing actually exists, or whether quantum effects smooth it out into something less pathological, we can't say. Rotating black holes are richer, stranger than non-rotating ones. They have structure, layers, regions with different properties. They're not just holes in space-time, they're dynamic, spinning engines of gravitational extremity, warping and twisting everything around them. Gravitational radiation carries energy away from orbiting systems, causing orbits to gradually decay. When massive objects orbit each other, especially when they orbit rapidly and closely, they create gravitational waves. These waves ripple outward through space-time, and they carry energy. That energy has to come from somewhere, and it comes from the orbital motion itself. As gravitational waves radiate away energy, the orbit loses energy. The objects spiral closer together. They orbit faster. This generates stronger gravitational waves which carry away more energy, which makes them spiral even closer. It's a runaway process, accelerating as the objects approach each other. For most orbiting systems, the effect is negligible. Earth and Sun generate gravitational waves, but so weakly that the energy loss is unmeasurable. The orbit won't decay noticeably over billions of years, but for compact, massive objects in close orbits, binary neutron stars, binary black holes, the effect is dramatic. The Hulse-Taylor binary pulsar, discovered in 1974, consists of two neutron stars orbiting each other every 7.75 hours. Observations over decades showed their orbital period decreasing by about 76 millionths of a second per year, exactly matching the energy loss predicted by gravitational wave emission. This was the first indirect evidence of gravitational waves, confirming Einstein's prediction decades before we detected the waves directly. The binary will eventually merge in about 300 million years, spiraling together in a final burst of gravitational radiation. We've now detected dozens of binary black hole and neutron star mergers, each one the end of a long spiral inward, driven by gravitational waves carrying orbital energy into space, its gravity radiating away its own energy, the universe ringing with the echoes of orbits decaying across cosmic time. The geodetic effect causes spinning objects to change their axis of rotation when moving through curved space-time. Imagine a gyroscope in orbit around Earth. It spins steadily, its axis pointing in a fixed direction. In flat space-time far from any mass, the axis would stay pointing that way forever, but space-time around Earth is curved, and that curvature affects the gyroscope in a subtle way. As it orbits through curved space-time, the gyroscope's spin axis slowly precesses, drifts, by a tiny amount each orbit. This is the geodetic effect, also called de Sitter precession. It's not friction or magnetic fields. It's purely the geometry of space-time. The gyroscope is following the straightest possible path through curved space, and that path gradually rotates the gyroscope's orientation. Measuring this effect was the goal of Gravity Probe B, one of the most precise experiments ever attempted. 4 gyroscopes, cooled to near absolute zero, housed in the most perfect spheres ever made, orbited Earth for over a year. The expected drift was about 6.6 arcseconds per year, roughly the width of a human hair viewed from 10 meters away. The experiment succeeded. The measured drift matched general relativity's prediction to within a few percent. Space-time curvature really does twist spinning objects, even when they're moving freely, following geodesics. It's a deeply strange result. The gyroscope isn't touching anything, isn't experiencing any forces. It's just moving through space-time, and the geometry itself rotates it. The shape of reality dictates orientation, not just position. Mass and energy are equivalent in general relativity, so even light and radiation contribute to gravitational fields. Einstein's famous equation, E equals mc squared, tells us mass and energy are interchangeable. But in general relativity, this has a deeper consequence. Anything with energy curves space-time, not just things with rest mass. A beam of light has no rest mass, but it has energy, and that energy contributes to space-time curvature. A photon creates its own gravitational field, however tiny. A hot object has more energy than a cold one, and therefore slightly more gravity. Even pure radiation, electromagnetic waves, gravitational waves, curves space-time. The early universe, filled with intense radiation, had its expansion influenced by the gravitational effects of that radiation. This is why, in general relativity, we talk about the stress-energy tensor, not just mass. It's a mathematical object that encodes all forms of energy, momentum, pressure, and stress. All of these contribute to space-time curvature. Practically, that the gravitational effects of non-mass energy are usually tiny. A laser beam's gravity is far too weak to measure, but near black holes, near neutron stars in the early universe, anywhere energy densities are extreme, these effects matter. It's a unification, really. Mass, energy, momentum, pressure, all are aspects of the same thing, all curve space-time, all contribute to what we experience as gravity. The universe doesn't distinguish. Anything that is, anything that has existence in the stress-energy sense, shapes the geometry of space-time. The no-hair theorem states that black holes are completely described by just three properties: mass, charge, and spin. Take two black holes with the same mass, charge, and angular momentum. According to the no-hair theorem, they're identical. Completely, perfectly identical. It doesn't matter how they formed. One might have formed from a collapsed star, the other from colliding neutron stars. One might have consumed mostly hydrogen, the other mostly iron. Doesn't matter. All the information about what fell in, every atom, every structure, every detail is erased. Only mass, charge, and spin remain. This is sometimes phrased poetically: black holes have no hair. Hair meaning distinguishing features, details, complexity. Black holes are bald, smooth, featureless except for those three numbers. Why? Because the event horizon hides everything inside. Whatever complexity existed in the matter that formed the black hole, whatever structure, whatever information, it's behind the horizon, inaccessible. The outside universe only knows what the black hole's gravitational field, electromagnetic field, and rotational frame-dragging reveal, and those fields are determined entirely by mass, charge, and spin. Most astrophysical black holes probably have negligible charge. Opposite charges neutralize quickly in space, so really they're described by just two numbers: mass and spin. It's both elegant and unsettling. Black holes are the simplest macroscopic objects in the universe, yet they form from the most complex processes: stellar collapse, galactic mergers. Complexity enters, simplicity remains. Information appears to be lost, though quantum mechanics insists it can't be. This tension is at the heart of the black hole information paradox. The no-hair theorem suggests black holes are nature's great erasers, reducing everything to just a few numbers. But maybe, somehow, the information is preserved in ways we don't yet understand. Wormholes are theoretical shortcuts through space-time, allowed by general relativity but likely requiring exotic matter to stay open. Einstein's equations allow for solutions called wormholes, tunnels through space-time connecting distant regions. Enter one mouth, travel through, emerge from the other mouth, possibly light years away, possibly in a different time. It sounds like science fiction, but the mathematics is sound. Wormholes are consistent with general relativity. The problem is keeping them open. A wormhole's throat, the narrowest part, wants to collapse. The curvature is so extreme that it naturally pinches shut. To hold it open, you'd need something with negative energy density, something that gravitationally repels rather than attracts. We call this exotic matter. Do we have exotic matter? Sort of. The Casimir effect, a quantum phenomenon, creates regions of negative energy density at tiny scales. But scaling that up to macroscopic sizes, to hold open a wormhole you could travel through, is probably impossible with known physics. Even if you could create a stable wormhole, traversing it might be problematic. Some solutions suggest the journey would take longer than just travelling the normal distance through space. Others suggest you'd encounter intense radiation or tidal forces, and if you tried to use it for time travel, connecting the two mouths so you could loop back to your own past, you'd likely create paradoxes, and the wormhole might become unstable. Wormholes are allowed, but unlikely. They're mathematical possibilities that physical reality probably forbids, at least at macroscopic scales. They're reminders that general relativity is permissive. It allows many strange geometries, but nature seems to be more restrictive than the equations alone. Still, we don't know for certain. Maybe somewhere, somehow, wormholes exist. Maybe the universe is riddled with shortcuts we haven't found. It's unlikely, but not impossible. And that tiny gap between unlikely and impossible is where wonder lives. The strong equivalence principle extends Einstein's insight to include all laws of physics, not just mechanics. Einstein's equivalence principle started with a simple observation. You can't distinguish between gravity and acceleration. In a windowless elevator, you couldn't tell if you're standing on Earth or accelerating through space at 9.8 meters per second squared. The strong equivalence principle goes further. It says that in a small enough region of space-time, falling freely in a gravitational field is completely indistinguishable from floating in deep space. Not just mechanically, for all physical laws, electromagnetism works the same, quantum mechanics works the same. Everything. This means there's no experiment you can perform in freefall that reveals you're in a gravitational field, at least not locally. Light behaves the same, atoms vibrate the same, time flows the same from your perspective. The laws of physics locally are the same everywhere. This is profound. It means gravity isn't a force that acts on objects. It's the structure of space-time itself, and when you're in free fall, you're moving naturally through that structure. You're not experiencing gravity, you're experiencing the absence of forces, following the straightest possible path through curved geometry. The strong equivalence principle is what allows us to do physics on the International Space Station, the same way we do it on Earth. The station is in free fall, and locally, within its hull, over short timescales. The laws of physics are identical to those in deep space. It's a kind of universality. The laws of nature don't care where you are or how you're moving. They're the same everywhere, for everyone in free fall. Gravity doesn't change the rules, it just changes the geometry in which the rules operate. Gravitational shielding is impossible in general relativity. You can't block gravity the way you can block electromagnetic fields. You can shield yourself from electric fields by surrounding yourself with a conductor. Electrons rearrange themselves by cancelling the external field inside. It's called a Faraday cage, and it works perfectly. You can shield yourself from magnetic fields with certain materials that redirect magnetic field lines around a region, creating a protected space inside. But there's no gravitational shielding. You can't block gravity. There's no material, no configuration, no trick that prevents gravitational effects from reaching you. Why? Because in general relativity, gravity isn't a force propagating through space. It's the curvature of space-time itself. Mass and energy curve space-time everywhere around them. That curvature is intrinsic to the geometry. You can't hide from geometry. Every form of mass and energy contributes to curvature. You can't create negative mass to cancel it out. Negative mass would actually increase the gravitational effects in strange ways. If it existed, which it probably doesn't. This is fundamentally different from other forces. Electromagnetism is mediated by photons that can be absorbed or reflected. Gravity is the shape of space-time, and you can't absorb or reflect shape. Science fiction often imagines anti-gravity devices, gravity shielding, ways to turn gravity off. But general relativity says no. Gravity is always on, always present, shaping everything. You can go into free fall to stop feeling it, but you can't make it go away. It's the most pervasive force in the universe precisely because it can't be blocked. It reaches everywhere, connects everything, shapes the cosmos from the smallest scales to the largest. The universe's critical density determines whether it will expand forever or eventually collapse back on itself. The universe is expanding, but gravity is pulling everything back together. Which wins? The answer depends on the universe's density. There's a critical density, about 5 atoms of hydrogen per cubic meter, averaged across all of space, that represents a perfect balance. If the universe's density is exactly critical, expansion will slow over time, approaching zero, but never quite stopping or reversing. If the density is higher than critical, gravity wins. Expansion will eventually stop and reverse. The universe will collapse back on itself in a big crunch, space-time contracting, everything falling together, perhaps to bounce into a new Big Bang. If the density is lower than critical, expansion wins. The universe will expand forever, gradually cooling, stars burning out, galaxies drifting apart, entropy increasing until heat death, a cold, dark, diffuse universe with no structure left. Measurements suggest the universe is remarkably close to critical density, so close that we can't tell if it's exactly critical, slightly above or slightly below. The geometry appears flat, which corresponds to critical density. But there's a twist. About 95% of the universe's energy comes from dark matter and dark energy, which we don't fully understand. Dark energy in particular drives accelerated expansion, overwhelming gravity at large scales. Current observations suggest the universe will expand forever, accelerating, driven by dark energy. But we don't know if dark energy is constant or changing. If it weakens, gravity might eventually win. If it strengthens, expansion might accelerate until even atoms are torn apart. A big rip. The universe's fate hangs on the critical density, on the balance between expansion and gravity, and on the mysterious nature of dark energy. We're living through the middle of the story and we don't yet know the ending. Gravitational collapse can be halted by degeneracy pressure in white dwarfs and neutron stars, but nothing stops it in black holes. When a star exhausts its fuel, gravity begins to win. The core contracts, heats up, and if the star is massive enough, different types of pressure can halt the collapse, at least temporarily. In white dwarfs, electron degeneracy pressure stops the collapse. This is a quantum effect. Electrons can't occupy the same quantum state, so when they're squeezed together, they resist further compression. This pressure doesn't depend on temperature, it's purely quantum mechanical. White dwarfs can cool indefinitely, becoming cold and dark, but they won't collapse further as long as they're below about 1.4 solar masses, the Chandrasekhar limit. For more massive cores, electron degeneracy pressure isn't enough. The collapse continues. Electrons and protons merge into neutrons, and neutron degeneracy pressure takes over. This creates a neutron star, essentially a giant atomic nucleus about 20 kilometers across. Neutron degeneracy can support up to about 2 to 3 solar masses, though the exact limit is uncertain. Beyond that, nothing can stop the collapse. No known pressure, quantum or otherwise, can resist gravity. The core collapses to a point, a singularity, and a black hole forms. This progression, electron degeneracy, neutron degeneracy, then nothing, represents the limits of matter's resistance to gravity. Quantum mechanics puts up a fight, but only to a point. Push hard enough, add enough mass, and gravity overwhelms everything. The structure of matter surrenders, and space-time itself collapses into a region from which nothing escapes. It's a hierarchy of capitulation. Matter resists, but gravity, given enough mass, always wins. And in winning, it creates the universe's most extreme objects, places where the rules break down, where our theories reach their limits. The cosmological constant, originally Einstein's biggest blunder, may actually exist as dark energy. In 1917, Einstein applied his new theory of general relativity to the entire universe. His equations predicted the universe should be either expanding or contracting, dynamic, changing. But astronomers at the time believed the universe was static, eternal, unchanging. To make his equations produce a static universe, Einstein added a term, the cosmological constant, often denoted by the Greek letter lambda. It represented a kind of energy inherent to empty space itself, creating a repulsive effect that could balance gravity and keep the universe static. Then, in 1929, Edwin Hubble discovered the universe is expanding. Galaxies are moving apart. The universe isn't static after all. Einstein abandoned the cosmological constant, reportedly calling it his biggest blunder. Fast forward to 1998. Astronomers studying distant supernovae discovered the universe's expansion is accelerating. Something is pushing space-time apart, overcoming gravity. We call it dark energy. And the simplest explanation is that Einstein's cosmological constant actually exists. The irony is rich. Einstein introduced it for the wrong reason, removed it when it seemed unnecessary, and decades later it returned for a different reason entirely. What he called his biggest blunder may be one of his most prescient ideas. Dark energy, possibly the cosmological constant, comprises about 68% of the universe's total energy. It's the dominant component driving the universe's evolution, and we have no idea what it fundamentally is. Is it energy of the vacuum? A new field? A sign that general relativity needs modification at cosmic scales? Einstein's blunder might be the key to understanding the universe's fate. Sometimes mistakes, revisited, become profound truths. Gravitational waves from the Big Bang might still be detectable as polarization patterns in the cosmic microwave background. The Big Bang wasn't just an explosion of matter and energy, it was space-time itself expanding, and that expansion generated gravitational waves, primordial ripples in the fabric of reality, created moments after the universe began. These primordial gravitational waves would have left an imprint on the cosmic microwave background, the light from 380,000 years after the Big Bang. Specifically, they would create a particular pattern in the polarization of that light, called B-mode polarization. Detecting this would be monumental. It would confirm that gravitational waves existed in the early universe. It would provide evidence for inflation, a rapid expansion in the universe's first fraction of a second, and it would be like hearing the universe's birth cry, delayed by 13.8 billion years but still echoing through space-time. Several experiments have searched for this signal. In 2014, the BICEP-2 experiment announced a detection, but further analysis showed the signal was mostly from dust in our own galaxy. The search continues. The signal, if it exists, is extraordinarily faint, a few parts per billion in the polarization pattern. Distinguishing it from foreground contamination requires exquisite precision and careful analysis. We may never detect primordial gravitational waves. They might be too weak, or inflation might not have generated detectable ones. But if we do find them, it would be one of the greatest discoveries in cosmology, direct evidence of what happened in the universe's first moments, and are written in the gravitational ripples that have travelled through all of cosmic history to reach us now. The mass gap refers to a mysterious absence of compact objects between 2.5 and 5 solar masses. When we catalogue neutron stars and black holes, we notice something odd. Neutron stars seem to max out around 2 to 2.5 solar masses. Black holes seem to start around 5 solar masses. In between, there's a gap, a range where we found very few compact objects. Is this gap real, or is it an observational bias? We're not sure. It might tell us something fundamental about how stars die and what happens during core collapse. One possibility: when a massive star's core collapses, there's a narrow mass range where the collapse is uncertain. Too light and neutron degeneracy pressure halts it, creating a neutron star. Too heavy and nothing stops it, creating a black hole. In between, the outcome might depend on details, rotation, magnetic fields, the exact composition, in ways that make objects in this range rare. Another possibility: objects do form in this range, but they're hard to detect. Isolated black holes don't emit light. Neutron stars might be dim if they're not pulsars. We might be missing them simply because they're difficult to find. In 2019, LIGO detected a gravitational wave event from a merger involving an object of about 2.6 solar masses, right in the gap. Was it a very heavy neutron star or a very light black hole? We don't know, but it suggests the gap might not be absolute. The mass gap is a puzzle, a hint that stellar death is more complex than we thought. It's a reminder that even in well-studied areas like stellar evolution, mysteries remain, or gaps in our knowledge waiting to be filled. Gravitational collapse in the early universe created the first black holes, possibly before the first stars even formed. The first stars formed a few 100 million years after the Big Bang, but black holes might have formed even earlier. In the dense, hot conditions of the early universe, regions slightly denser than average could have collapsed directly into black holes, bypassing the stellar stage entirely. These primordial black holes could have masses ranging from tiny, less than an asteroid, to huge, thousands of solar masses. If they exist, primordial black holes could explain some puzzles. Small ones might comprise some or all of the dark matter. Large ones might have seeded the supermassive black holes we see at galactic centers, giving them a head start on growth. Yet detecting primordial black holes is difficult. Small ones would be dark, compact, nearly impossible to see directly, but they'd reveal themselves through gravitational effects, lensing, orbital perturbations, or through Hawking radiation if they're small enough. Some gravitational wave detections hint at black holes more massive than we'd expect from stellar collapse, possibly pointing to primordial origins. But the evidence is ambiguous. We don't yet know if primordial black holes are common, rare, or non-existent. The idea is tantalizing, though. Black holes older than stars formed from the quantum fluctuations of the Big Bang itself, sculpted by the universe's earliest moments of gravity and expansion. Relics from a time before light, before atoms, before anything we'd recognize. Gravity's first victories, etched into space-time when the cosmos was still in its infancy. The firewall paradox suggests that quantum mechanics and general relativity predict contradictory experiences at black hole event horizons. According to general relativity, crossing the event horizon of a large black hole should be uneventful. You wouldn't feel anything special. Locally, space-time is smooth. You pass through and only later realize you can't escape. But quantum mechanics suggests something different. Hawking radiation, the slow evaporation of black holes through quantum effects, seems to require that information escaping the black hole be encoded in the radiation. For this to work, some physicists argue, there must be intense quantum correlations at the event horizon, so intense that they'd form a firewall of high-energy particles that would incinerate anything trying to cross. This creates a paradox. General relativity says crossing is smooth. Quantum mechanics says crossing might be catastrophic. Both can't be right. This paradox goes deeper than just a disagreement about what you'd experience. It touches fundamental questions. Is information lost in black holes? How do quantum mechanics and general relativity reconcile? What happens at event horizons where both theories must apply? Some propose solutions. Maybe the firewall doesn't exist, and information escapes in subtle ways we don't understand. Maybe general relativity needs modification at quantum scales. Maybe black holes evaporate before firewalls form. Maybe the paradox reveals that space-time itself is emergent, constructed from quantum entanglement in ways we're only beginning to grasp. The firewall paradox is unresolved. It sits at the boundary between our two greatest theories, pointing to gaps in our understanding. Someday, a theory of quantum gravity will resolve it. Until then, it's a reminder that black holes aren't just extreme objects, They're laboratories where our theories collide. Hawking radiation proposes that black holes aren't truly black, but slowly evaporate by emitting quantum particles. In 1974, Stephen Hawking showed that black holes aren't entirely black. They emit radiation, thermal radiation, like the glow from a hot object, through a quantum effect near the event horizon. So here's the mechanism. Quantum mechanics allows particle-antiparticle pairs to spontaneously appear in empty space, existing briefly before annihilating. Near a black hole's event horizon, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is emitting particles, Hawking radiation. The energy for this radiation comes from the black hole's mass. As it radiates, the black hole loses mass. It shrinks. The smaller it gets, the hotter it becomes, and the faster it radiates. Eventually it evaporates completely. For stellar mass black holes, this process is unimaginably slow. A black hole with the sun's mass would have a temperature of about 60 billionths of a Kelvin, far colder than the cosmic microwave background. It would absorb more radiation than it emits, growing rather than shrinking. Its evaporation time would be about 10 to the power of 67 years, far longer than the current age of the universe. But smaller black holes radiate faster. A black hole the mass of a mountain would evaporate in about the age of the universe. A tiny primordial black hole could be evaporating right now, ending its life in a burst of radiation. Hawking radiation has never been directly observed. It's too faint for any black hole we can detect. But it's almost certainly real. It connects thermodynamics, quantum mechanics, and general relativity in profound ways. And it suggests that even black holes, the universe's ultimate prisons, eventually release everything given enough time. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary surface. One of the strangest ideas to emerge from studying black holes is the holographic principle. It arose from a puzzle. The entropy of a black hole, a measure of how much information it contains, is proportional to the area of its event horizon, not its volume. This is weird. Normally we'd expect the information content of a region to scale with its volume. A bigger box can hold more books. But for black holes, it scales with surface area. It's as if all the information inside is somehow encoded on the two-dimensional boundary. Physicists began to wonder if this applies more generally. Perhaps all the information in any three-dimensional region of space can be encoded on its two-dimensional boundary. The interior, in a sense, is a hologram, a three-dimensional projection of information stored on a surface. This isn't metaphor. It's a concrete proposal about the nature of reality. If true, it means the dimension of space might be different from what we experience. The three-dimensional world we inhabit might be a kind of illusion, reconstructed from information encoded in fewer dimensions. The holographic principle has found mathematical support in string theory, particularly in something called the ADS/CFT correspondence, which shows that certain gravitational theories in higher dimensions are mathematically equivalent to non-gravitational theories on their boundaries. It's deeply counterintuitive. You feel three-dimensional. You move through 3 dimensions of space. But the holographic principle suggests this might be emergent, constructed from a more fundamental description that lives on a boundary we never see. It's too early to say if this is how the universe really works, but it's a profound shift in thinking, one that challenges our most basic assumptions about space, information, and what it means for something to exist. Loop quantum gravity attempts to reconcile general relativity and quantum mechanics by quantizing space-time itself. General relativity describes space-time as smooth, continuous, infinitely divisible. Quantum mechanics describes everything else as discrete, quantized, existing in packets. Loop quantum gravity tries to apply quantum mechanics to space-time itself. The core idea is that space isn't continuous. At the smallest scales, the Planck scale, about 10 to the power of minus 35 meters. Space-time is made of discrete loops, tiny woven structures sometimes called spin networks. Space is quantized, existing in minimal units. These loops aren't embedded in space, they are space. They connect and interact, and from their collective behavior, the smooth space-time we experience at larger scales emerges, like a fabric woven from individual threads. In loop quantum gravity, areas and volumes come in discrete units. You can't have half a Planck volume, it's the smallest possible volume. This quantization might prevent singularities. Where general relativity predicts infinite density at the center of black holes or at the Big Bang, loop quantum gravity suggests the collapse halts at Planck density, perhaps bouncing into expansion. Loop quantum gravity is mathematically rigorous and doesn't require extra dimensions like string theory does. But it's also incomplete. It doesn't yet incorporate matter and forces other than gravity. It makes few testable predictions so far. And still, it's a serious attempt to answer one of physics' deepest questions. What is space-time made of? If loop quantum gravity is right, space-time is woven from quantum loops, and the smooth geometry we experience is an approximation, a large-scale average of something fundamentally discrete and quantum underneath. The gravitational constant g may not actually be constant, but could vary with time or location in the universe. The gravitational constant g appears in Newton's and Einstein's equations as a fixed number, the strength of gravity. We assume it's the same everywhere, and has been the same throughout cosmic history. But what if it's not? What if g varies, even slightly, across space or time? Some theories, particularly those attempting to unify gravity with other forces, suggest fundamental constants might actually change. If the strength of gravity varied over billions of years, it would affect stellar evolution, planetary orbits, the expansion of the universe. Ancient light from distant galaxies might reveal hints of a different g. So far, measurements show g as constant to within very tight limits. Studies of the cosmic microwave background, binary pulsars, and ancient rocks containing radioactive elements all constrain how much g could have changed. The limits are strict, less than a few parts per trillion per year, if at all. But g is also one of the least precisely measured fundamental constants. Different laboratory experiments give slightly different values, variations of about 0.05%, far larger than their stated uncertainties. This isn't evidence that g varies, it's more likely experimental error. But it's frustrating. After more than 2 centuries since Cavendish first measured it, we still struggle to pin down its value precisely. Perhaps g truly is constant, a fixed property of the universe, or perhaps it varies in ways too subtle for us to detect yet. Either way, it's worth checking. If G varies, it would revolutionize our understanding of gravity and the universe's evolution. Even negative results teach us something. They constrain theories, narrow possibilities, guide us toward truth. Binary pulsars provide the most precise tests of general relativity, confirming its predictions to extraordinary accuracy. Pulsars are rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. Some pulsars orbit companion stars, forming binary systems. These systems are natural laboratories for testing general relativity with extraordinary precision. The Hulse-Taylor binary pulsar, discovered in 1974, consists of two neutron stars orbiting each other every 7.75 hours. Pulsars are incredibly stable clocks. Some keep time better than atomic clocks. By tracking the pulsar's radio pulses over years, astronomers can measure its orbit with remarkable accuracy. General relativity makes precise predictions for such systems. The orbit should precess, time should dilate, and gravitational waves should carry away energy, causing the orbit to decay. All of these effects are measurable, and they match. The orbital decay agrees with gravitational wave emission predictions to better than 0.2% accuracy. The precession matches, the time dilation matches, and every prediction general relativity makes is confirmed over and over year after year. Since then, we've discovered other binary pulsars, including a double pulsar system where both neutron stars are pulsars. These provide even more stringent tests. General relativity passes everyone. Binary pulsars are gravity in extremis, strong fields, high velocities, relativistic effects amplified. They're the most precise test beds we have for general relativity outside of gravitational wave detections, and they show conclusively that Einstein's century-old theory describes gravity with stunning accuracy, even in the most extreme environments we can observe. Gravitational instantons are mathematical solutions describing quantum tunneling events in space-time itself. In quantum mechanics, NUS particles can tunnel through barriers, appearing on the other side of obstacles they shouldn't classically be able to cross. Gravitational instantons apply this idea to space-time itself. An instanton is a solution to Einstein's equations in imaginary time, a mathematical trick that lets physicists study quantum tunneling. In this framework, space-time can tunnel from one configuration to another, jumping between states that would be classically forbidden. One famous example is the Hawking-Moss instanton, which describes how the early universe might have tunneled from a false vacuum to a true vacuum during inflation. Another is the possibility that the universe itself tunneled into existence from nothing, no space, no time, no matter, through a quantum fluctuation. These ideas are speculative, are sitting at the edge of what we can meaningfully discuss. They require combining quantum mechanics and general relativity in ways we don't fully understand. They involve concepts, imaginary time, quantum tunneling of space-time, that challenge our intuitions about what's possible. But they're mathematically consistent solutions to the equations. They suggest that space-time itself might have quantum properties, that the very fabric of reality might obey quantum rules, able to fluctuate, tunnel, and transition between states. If gravitational instantons are real, if space-time can tunnel, then the universe's origin might be a quantum event, requiring no cause, no prime mover, just the inherent quantum fuzziness of reality, allowing something to emerge from nothing. It's a dizzying idea, and perhaps it's wrong. But it's one of the few frameworks we have for thinking about how existence itself might have begun. The multiverse hypothesis posits that the strength of gravity might vary between different universes. In some interpretations of quantum mechanics and cosmic inflation, our universe might be just one among countless others, a multiverse. If so, different universes might have different physical constants, including the strength of gravity. In most of these hypothetical universes, gravity would be wrong for life, too strong and stars would burn out quickly, or atoms couldn't form, too weak and matter wouldn't clump into stars and galaxies at all. The universe would remain a diffuse, cold fog. Our universe has gravity in a narrow range that allows complexity. Stars that burn for billions of years, planets that orbit stably, just structures that evolve. This might be selection bias. We exist in a universe where gravity permits our existence. In universes where it doesn't, there's no one to ask the question. This is the anthropic principle. The universe appears fine-tuned for life because if it weren't, we wouldn't be here to observe it. It's unsatisfying to some. It feels like giving up on explaining why gravity has the strength it does. But if the multiverse is real and constants vary randomly, the anthropic principle might be the only explanation we can get. We have no direct evidence for other universes. The multiverse might be untestable, unfalsifiable, more philosophy than science. Or maybe someday we'll find indirect signatures, anomalies in the cosmic microwave background, hints of collisions with other universes. For now, it remains speculative, but it raises profound questions. Why is gravity as strong as it is? Is it accident, necessity, or selection? And are we alone in the vastness of reality, or just one island in an infinite ocean of universes, each with its own version of gravity? Gravitational entropy, or the disorder associated with gravitational systems, tends to increase over cosmic time. Entropy is often described as disorder, but more precisely, it's the number of ways a system can be arranged. High entropy means many possible arrangements. Low entropy means few. The early universe had low gravitational entropy. Matter was almost perfectly smooth, evenly distributed. This seems orderly, and it is, gravitationally speaking. A smooth distribution represents a very specific low-entropy configuration. But over time, gravity amplified tiny fluctuations. Near matter clumped into stars, galaxies, galaxy clusters. The universe became lumpier, more structured. This seems like increasing order, but gravitationally it's increasing entropy. Why? Because clumpy distributions have higher entropy than smooth ones when gravity is involved. There are many more ways to arrange matter into clumps than to spread it evenly. A galaxy with its complex distribution of stars has high gravitational entropy. A black hole, the ultimate clump, has the highest entropy for its mass. This is counterintuitive. We think of galaxies and stars as ordered, organized, and they are, thermodynamically. But gravitationally, they represent entropy increasing, the universe exploring more and more configurations as gravity pulls matter together. Ultimately, if the universe expands forever, a gravitational entropy will continue increasing. black holes will evaporate, matter will disperse, and the cosmos will approach maximum entropy, a state of equilibrium where nothing interesting happens anymore. Heat death. But we're far from that. The universe is still young, still organizing, still increasing its entropy. Stars still shine, galaxies still merge, black holes still grow. We're living in the middle chapters, where gravity is still doing its work, building complexity even as it marches toward eventual uniformity. Neutron star mergers create gravitational waves and electromagnetic signals, allowing us to measure cosmic expansion rates. When two neutron stars spiral together and merge, they create a spectacular event. Both gravitational waves rippling through space-time and a brilliant flash of electromagnetic radiation across multiple wavelengths, from gamma rays to radio. This dual signal, gravity and light, makes neutron star mergers unique. Gravitational waves tell us the distance to the merger. They're standard sirens, much like standard candles in astronomy. By analysing the waveform, we can infer how far away the event occurred. The electromagnetic signal tells us the redshift, how much the universe has expanded since the light was emitted. By measuring which galaxy the merger occurred in, we can determine how fast that galaxy is receding. Distance and recession speed together give us the Hubble constant, the rate of cosmic expansion. This is an independent way to measure it, as not relying on the cosmic distance ladder or cosmic microwave background analyses. In 2017, the first neutron star merger detected in both gravitational waves and light, GW170817, provided exactly this measurement. It gave a Hubble constant value intermediate between values from other methods, which currently disagree by a few percent. This Hubble tension is one of cosmology's current puzzles. More neutron star merger detections will refine this measurement, potentially resolving the tension or revealing new physics. These mergers are cosmic Rosetta Stones, carrying information in multiple languages, gravity and light, allowing us to read the universe's expansion history in new ways. The self-force problem describes how a particle's own gravitational waves affect its motion through curved space-time. When an object orbits in curved space-time, say a small black hole orbiting a larger one, it generates gravitational waves. Those waves carry energy and angular momentum away from the system, causing the orbit to decay. But there's a subtlety. The gravitational waves the object creates also affect the object itself. The waves curve space-time nearby, and the object responds to that curvature. It feels its own gravitational influence, a self-force. Calculating this is fiendishly difficult. You have to track how the object curves space-time, how that curvature propagates as waves, and how those waves back-react on the object's motion, all self-consistently. It's a problem of enormous computational complexity. For in spiraling black holes, especially small ones orbiting large ones called extreme mass ratio in spirals, the self-force matters. It affects the orbit's evolution, the gravitational wave signal's precise shape. To extract science from gravitational wave detections of such systems, we need accurate self-force calculations. Researchers have spent decades working on this, developing sophisticated numerical methods and analytical approximations. It's a problem where general relativity's nonlinearity, gravity gravitates, creates mathematical challenges that push our computational abilities. The self-force is subtle, usually a small correction. But in precision gravitational wave astronomy, small corrections matter. They encode information about space-time structure, black hole properties, and the nature of gravity itself. Getting them right is essential for testing general relativity in the strong field regime. It's humbling in a way. Or even our best theory of gravity presents computational challenges we're still working to overcome. Understanding gravity doesn't just mean writing equations, it means solving them, and some solutions require extraordinary effort. Gravitational memory is a permanent displacement of test particles after a gravitational wave passes through. Usually we think of gravitational waves as transient. They pass through, stretching and squeezing space-time briefly, then leave everything as it was. But these are not quite true. After a gravitational wave passes, test particles, objects in free fall, don't return to their original positions. They're permanently displaced by a tiny amount. This persistent change is called gravitational memory, or the memory effect. Why does this happen? A gravitational wave carries energy and momentum. As it passes, it changes the space-time geometry in its wake, leaving a permanent memory of its passage. The displacement is small, far smaller than the wave's oscillatory stretching and squeezing, but it's permanent. There are different types of memory: ordinary memory from the wave's oscillations, and null memory from the wave's permanent change to space-time structure. Both are real and, in principle, detectable. Detecting gravitational memory is difficult. It requires tracking the positions of test masses over long times, isolating a tiny permanent displacement from much larger oscillatory signals and noise. LIGO and other detectors haven't definitively detected it yet, but future detectors might. Gravitational memory is a reminder that waves aren't just transient disturbances. They leave traces, permanent alterations to space-time structure. The universe remembers what passed through it, even if the memory is faint, a whisper of geometry changed forever. Naked singularities would be points of infinite density without event horizons, visible to the outside universe. Black holes hide their singularities behind event horizons. Whatever strange, perhaps infinite phenomena occur, the singularity remains sealed off, invisible to the outside universe. But what if a singularity could exist without an event horizon, naked, exposed, visible? This possibility troubles physicists. A naked singularity would be a place where space-time curvature becomes infinite, where our equations break down, where predictability fails, and we could see it. We could, in principle, send signals to it and receive signals back. It would violate what's called cosmic censorship, the idea that nature always hides singularities behind horizons, protecting the rest of the universe from their pathologies. Roger Penrose proposed the cosmic censorship conjecture in 1969, suggesting that naked singularities can't form from realistic gravitational collapse. If true, it means whenever matter collapses to infinite density, an event horizon always forms first, cloaking the singularity from view. But proving cosmic censorship has been difficult. There are mathematical solutions to Einstein's equations that contain naked singularities, though they require special, perhaps unrealistic conditions. Whether nature actually forbids them remains an open question. If naked singularities exist, they'd be deeply troubling. They'd represent places where general relativity predicts its own failure, and that failure would be visible, influencing the outside universe in unpredictable ways. Or perhaps quantum gravity prevents singularities altogether, smoothing them into something less pathological. For now, cosmic censorship remains unproven but widely believed. Nature seems to hide her infinities, keeping the worst extremes of gravity safely behind horizons. Whether that's fundamental law or happy accident, we don't yet know. The averaging problem in cosmology questions whether we can treat the universe's lumpy matter distribution as smooth for gravitational calculations. When cosmologists model the universe, they usually assume it's homogeneous and isotropic, the same everywhere on average, and the same in all directions. Yeah, this is called the cosmological principle, and it simplifies the mathematics enormously. But the universe isn't actually smooth, it's lumpy, full of galaxies, clusters, voids. At small scales, matter is distributed very unevenly, so cosmologists average, treat the lumpiness as small perturbations on a smooth background, and calculate gravity's effects on the smooth part separately from the lumpy part. The question is, does this averaging work? Is the gravity of the average distribution the same as the average of the gravity? In general relativity, the answer is no. Gravity is nonlinear. It doesn't obey superposition like electromagnetism. The curvature from a smooth distribution differs from the average curvature of a lumpy distribution. The difference is called back reaction. How big is back reaction? Could it affect the universe's expansion rate? Could some of what we attribute to dark energy actually be back reaction from the lumpiness we averaged away? Most cosmologists think back reaction is small, a few % effect at most. But calculating it precisely is difficult. Some researchers argue it could be significant, potentially affecting our interpretation of cosmic acceleration. The averaging problem is subtle and technical, but it touches something fundamental. Are our cosmological models accurate? Are we justified in treating the universe as smooth? Or are we missing something by ignoring the details of how matter clumps and how that clumping affects gravity? It's a reminder that even our large-scale models involve approximations, and approximations sometimes hide surprises. Gravitational thermodynamics assigns temperature and entropy to event horizons, connecting gravity to quantum mechanics. Black holes have temperature. This seems absurd. How can something from which nothing escapes be hot? But according to Hawking's calculations, black holes emit thermal radiation at a temperature inversely proportional to their mass. A stellar mass black hole is incredibly cold, billionths of a degree above absolute zero. A supermassive black hole is even colder. But smaller black holes are hotter. A black hole the mass of a small asteroid would have a temperature of billions of degrees. Temperature implies entropy, a measure of disorder or hidden information. Black holes have entropy proportional to their event horizon's area. This is the Beakenstein-Hawking entropy, and it's huge. Stellar mass black hole contains more entropy than all the stars, planets, and gas in a large galaxy. This connection between gravity and thermodynamics is profound. It suggests that space-time itself has thermodynamic properties, that event horizons are like surfaces with temperature and entropy, obeying laws analogous to the laws of thermodynamics. The first law of black hole mechanics resembles the first law of thermodynamics. Energy is conserved. The second law states that the total area of event horizons never decreases, analogous to entropy never decreasing. There are even third and zeroth laws with thermodynamic analogues. This isn't just analogy, it's deep physics, hinting that gravity and thermodynamics are connected at a fundamental level. Some physicists believe gravity might be an emergent phenomenon, arising from thermodynamics or information theory rather than being fundamental. Gravitational thermodynamics suggests that entropy, information, and space-time structure are intimately related. Event horizons aren't just boundaries, they're thermodynamic objects holding information possessing temperature, obeying laws that bridge quantum mechanics and gravity. A DS/CFT correspondence suggests that gravity in higher dimensional space is mathematically equivalent to non-gravitational physics on its boundary. In 1997, physicist Juan Maldacena discovered an astonishing relationship. A gravitational theory in a higher dimensional space, anti-de Sitter space, or ADS, is mathematically equivalent to a quantum field theory without gravity on that space's boundary. A conformal field theory, or CFT. It's called the ADS/CFT correspondence, and it's one of the most important ideas in theoretical physics. It's a concrete realization of the holographic principle. The physics in a volume of space is encoded on its boundary. What makes it powerful is that it's a duality, a dictionary for translating between two completely different-looking theories. Difficult problems in one theory can sometimes be solved by translating to the other theory, where they're easier. It's been used to study quantum properties of black holes, to model quark-gluon plasmas created in particle accelerators, to explore quantum entanglement. It connects gravity to quantum mechanics in a precise mathematical way. There's a catch. It applies to anti-de Sitter space, which has negative curvature, like a saddle. Our universe has flat or positive curvature and is expanding. So ADS/CFT doesn't directly describe our reality, but it's still deeply valuable. It shows that gravity can emerge from non-gravitational theories, that space-time dimension might not be fundamental, that the holographic principle is mathematically consistent. It hints that gravity isn't truly fundamental. It's emergent from deeper quantum structures. A DS/CFT is a window into quantum gravity, even if it's not our universe's quantum gravity. It teaches us that gravity and quantum mechanics can be reconciled, that space-time can arise from information, that reality's structure might be stranger and richer than we imagined. Massive gravitons would mean gravity has finite range rather than being truly long distance, changing cosmology entirely. In general relativity, gravity is mediated by space-time curvature, not by particles. But quantum field theory describes forces as mediated by particles, photons for electromagnetism, gluons for the strong force. If gravity is quantum mechanical, it should have a particle too, the graviton. Standard theory assumes gravitons are massless, travelling at the speed of light with infinite range. But what if they have mass, even a tiny mass? Massive gravitons would change everything. Gravity would have finite range. Beyond a certain distance, gravitational effects would fade faster than the inverse square law predicts. Orbits at large distances would behave differently. The universe's expansion might follow different rules. Massive gravitons would also give gravity additional degrees of freedom, 5 polarization states instead of 2. This would affect gravitational wave signals, providing a way to test whether gravitons have mass. Experiments constrain graviton mass to be incredibly tiny, less than about 10 to the power of minus 32 electron volts, if it exists at all. This corresponds to a range of billions of light years or more, so local gravity wouldn't change noticeably. But cosmology might. Some modified gravity theories propose massive gravitons to explain cosmic acceleration without dark energy. If gravity weakens at large scales, expansion could accelerate without needing a cosmological constant. So far, observations favour massless gravitons. Gravitational wave detections show gravity travels at light speed, consistent with massless gravitons. But the constraints keep improving, and testing graviton mass remains an active area of research. It's a fundamental question. Is gravity's range truly infinite? Or does it have a cut-off we haven't detected yet? The answer shapes how we understand gravity's role in the cosmos. The Unruh effect predicts that accelerating observers detect thermal radiation even in otherwise empty space. Imagine you're floating in deep space, far from any matter or radiation. You detect nothing. Perfect vacuum, perfect silence. Now imagine you accelerate. According to the Unruh effect, you'd suddenly detect thermal radiation, a bath of particles at a temperature proportional to your acceleration. The vacuum isn't empty anymore, it's warm. This seems impossible. How can acceleration create particles? But the Unruh effect is a consequence of quantum field theory and curved or accelerated reference frames. What looks empty to an inertial observer looks thermal to an accelerating observer. It's not that particles are created, it's that the concept of particle is observer-dependent. The Unruh effect connects deeply to Hawking radiation. An observer hovering just above a black hole's event horizon must accelerate intensely to stay in place, fighting gravity. That acceleration means they detect Unruh radiation, which is mathematically related to the Hawking radiation the black hole emits. The effect is extraordinarily weak. To detect a temperature of 1 Kelvin, you'd need to accelerate at about 10 to the 20 meters per second squared, roughly a billion times Earth's gravity. We can't achieve accelerations remotely close to this, so the Unruh effect has never been directly observed. But it's profound theoretically. It shows that concepts like particle and vacuum depend on your state of motion. It connects acceleration to temperature, gravity to thermodynamics. It's another hint that space-time, quantum mechanics, and thermodynamics are deeply intertwined in ways we're still learning to understand. Gravitational anomalies in quantum field theory initially threatened consistency, but ultimately constrained possible particle theories. In quantum field theory, anomalies are places where classical symmetries break down at the quantum level. Sometimes anomalies are fine. They lead to interesting physics, but sometimes they're disastrous, making the theory inconsistent, unable to make sensible predictions. Gravitational anomalies arise when you try to combine quantum field theory with curved space-time, and certain combinations of particles create anomalies that violate energy conservation or make probabilities not add up to 1. Clear signs of inconsistency. In the 1970s, physicists discovered that the standard model of particle physics could have gravitational anomalies. This was alarming. If the standard model were anomalous, it couldn't be a consistent quantum theory in curved spacetime. But then they calculated more carefully. The anomalies from different particles, quarks and leptons, cancel each other exactly, but only if the particles come in the precise combinations the standard model contains. The three families of quarks and leptons, with their specific charges and colours, cancel all gravitational anomalies perfectly. This was stunning. Anomaly cancellation wasn't built in, it emerged from the particle content. It provided evidence that the standard model's structure isn't arbitrary. The particles and their properties had to be precisely what they are, or the theory would be inconsistent. Before the top quark was discovered, anomaly cancellation predicted it must exist to cancel the bottom quark's contributions. When the top quark was found, it confirmed the prediction. Gravitational anomalies, initially a threat, became a tool, a constraint that helped physicists understand why the standard model has the structure it does. Sometimes what looks like a problem points toward deeper understanding. The positive energy theorem proves that the total energy in general relativity can never be negative, preventing certain paradoxes. In general relativity, defining the total energy of a system is tricky. Or energy isn't localized. You can't point to a spot and say, the energy is here. Gravitational energy is especially subtle. It can be positive or negative depending on your reference frame. But there's a global notion, the total energy of an isolated system measured from far away. And in the 1970s and 80s, physicists proved the positive energy theorem. This total energy is always non-negative. It's zero only for completely empty flat space-time and positive for anything else. This might seem obvious, but it's not. General relativity allows solutions with weird energy distributions, and there was no guarantee total energy couldn't be negative. Why does this matter? Negative total energy would create paradoxes. You could extract infinite energy from gravitational fields, violating conservation laws. The universe could be unstable, only spontaneously creating matter and energy without bound. The positive energy theorem rules this out. It guarantees that general relativity is stable, that you can't extract infinite energy, that space-time configurations have a sensible notion of energy that respects physical intuition. The proof is mathematically sophisticated, involving spinors, manifolds, and techniques from differential geometry. But the result is fundamental. Gravity can't be used to create energy from nothing. The universe has a flaw, a lowest energy state, and that prevents certain pathological behaviors. It's a consistency check that general relativity passes. The theory doesn't just describe gravity, it does so in a way that respects deep principles like energy conservation, at least globally, even if local energy density is ambiguous. Quantum gravity corrections might prevent the formation of true singularities, replacing black hole centers with exotic structures. General relativity predicts singularities, points of infinite density and curvature at black hole centers and at the Big Bang. But infinity is usually a sign that a theory has reached its limits, that new physics must take over. Quantum mechanics abhors infinities too. It smooths out classical sharpness, spreads probability, limits how concentrated things can be. So quantum gravity, the elusive theory combining general relativity and quantum mechanics might eliminate singularities. One proposal: Planck stars. At the Planck scale, 10 to the power of minus 35 meters, 10 to the power of minus 43 seconds, quantum effects dominate. Perhaps collapsing matter can't compress beyond Planck density. Instead of forming a singularity, it bounces. Quantum pressure halts the collapse, creating a tiny, ultra-dense object that might later explode. Another proposal: fuzzballs from string theory. Instead of a singularity and event horizon, a black hole might be a tangle of strings. No horizon, no singularity, just a highly excited quantum state that looks like a black hole from outside. Or wormholes connecting the black hole interior to another region of space-time, or baby universes budding off, or any number of exotic possibilities allowed by speculative quantum gravity theories. We don't know which, if any, is correct. We have no experimental access to Planck-scale physics or black hole interiors. These are educated guesses, extrapolations from theories that aren't yet complete. But the common thread is this: singularities probably aren't real. They're artifacts of pushing general relativity too far into regimes where quantum effects must matter. When we finally understand quantum gravity, singularities will likely dissolve into something strange but finite. The universe might be extreme, but perhaps it's not infinite. Emergent gravity theories propose that space-time curvature arises from more fundamental quantum entanglement. What if gravity isn't fundamental? What if space-time curvature, the thing we call gravity, emerges from something deeper? Some physicists propose that gravity emerges from quantum entanglement, the spooky correlations between quantum particles. In this view, space-time itself is woven from entanglement. The geometry, how far apart things are, how space-time curves, is determined by how quantum systems are entangled. Change the entanglement, and space-time changes. Strong entanglement might correspond to connected regions of space. Weak entanglement might correspond to distant regions. Curvature might arise from patterns in how entanglement is distributed. This isn't just philosophy, it's motivated by concrete results. In ADS/CFT correspondence, entanglement entropy in the boundary theory is related to the area of surfaces in the bulk spacetime. The famous ER equals EPR conjecture suggests entangled particles are connected by wormholes. Spooky action at distance as geometric connection. If true, emergent gravity would mean space-time is like temperature or pressure, a large-scale property that emerges from microscopic quantum behavior. Just as temperature emerges from molecular motion, space-time might emerge from quantum entanglement. This is highly speculative. We don't have a complete theory of emergent gravity, but it's a compelling idea. Gravity as secondary, space-time as constructed, geometry as consequence rather than foundation. If gravity is emergent, then asking, what is space-time made of, has an answer. Quantum information, entanglement, the relationships between quantum systems. And curvature, gravity itself, is just the shape those relationships take when viewed from a macroscopic perspective. The problem of time in quantum gravity arises because general relativity doesn't have a universal time coordinate. In quantum mechanics, time is special. It's the backdrop against which everything evolves. You solve the Schrödinger equation to find how a quantum state changes in time. Time is external, absolute, ticking forward while quantum systems evolve, but in general relativity, time isn't special. It's woven together with space into space-time, curved and warped by matter and energy. There's no universal clock, no privileged time coordinate. Different observers experience time differently. Time itself is dynamic, part of the geometry that's being shaped by gravity. This creates a profound problem when we try to combine quantum mechanics and general relativity. Quantum mechanics demands a time parameter to evolve in. General relativity says there's no such thing. Time is relational, emergent, observer-dependent. This is called the problem of time, and it's one of the deepest puzzles in quantum gravity. If you try to write down a quantum theory of the entire universe, including space-time itself, you can't ask, how does the universe evolve in time? Because there's no external time for it to evolve in. And some approaches suggest time is emergent, arising only when you look at subsystems, not the whole. Others propose timeless quantum states. The universe simply is, in some eternal sense, and our experience of time flowing is a consequence of how we're embedded in it. Loop quantum gravity, string theory, and other quantum gravity approaches all struggle with this problem in different ways. None has fully resolved it. It's humbling. Time feels so fundamental, so obvious. Yet when we try to understand the universe at its deepest level, time becomes slippery, perhaps even illusory. The ticking of clocks, the flow of moments, these might be emergent properties, not fundamental features of reality. Causal set theory suggests space-time is fundamentally discrete, built from point-like events with causal relationships. What if space-time isn't continuous? What if, at the smallest scales, it's made of discrete points, individual events, each one happening or not happening, with no in-between? Causal set theory proposes exactly this. Space-time is a collection of point-like events, and the only structure connecting them is causality, whether one event could influence another. If event A could send a signal to event B, they're causally related. If not, they're not. From this minimal structure, just events and their causal relationships, the theory claims that space-time dimension and geometry emerge statistically. Count how many events lie in a region's causal past, and you can infer its space-time volume. Count the pattern of causal relationships, and you can reconstruct whether space-time is curved or flat, how many dimensions it has. It's beautifully minimal. No coordinates, no metric, no equations of motion, just discrete events and the estion. Which events could affect which others? The discreteness is fundamental. There's a minimal volume of space-time, a smallest event. You can't subdivide forever. Space and time come in atoms, causally connected dots that, when viewed from afar, blend into the smooth space-time we experience. Causal set theory makes some predictions. Space-time discreteness might introduce tiny fluctuations, potentially detectable in how particles scatter or how light propagates across cosmic distances. So far, no clear signals, but the search continues. It's a radical rethinking. Space-time as a giant, causally structured network of discrete events. Not embedded in anything, not flowing through time, just existing as a web of influence. With everything we experience, distance, duration, geometry, emerging from the pattern of connections. The black hole information paradox challenges whether information is preserved or destroyed when matter falls into black holes. Quantum mechanics has a fundamental principle. Information is conserved. If you know a system's complete quantum state at one time, you can, in principle, reconstruct any past or future state. Information can be scrambled, hidden, spread out, but never destroyed. But what happens when something falls into a black hole? The object crosses the event horizon and disappears from the outside universe. Eventually, the black hole evaporates through Hawking radiation, which is thermal, random, carrying no information about what fell in. When the black hole is gone, where did the information go? Is it destroyed, violating quantum mechanics? Or is it somehow encoded in the Hawking radiation, preserved in ways too subtle for us to detect? This is the black hole information paradox, and it's troubled physicists since Hawking discovered his radiation in the 1970s. General relativity says information is lost. Quantum mechanics says it can't be. Both theories seem ironclad within their domains. Proposed solutions abound. Maybe information is encoded on the event horizon and gradually released in the radiation's subtle correlations. Maybe black holes have soft hair, additional structure that stores information. Maybe the interior and radiation are entangled in complex ways. Maybe space-time itself is modified near horizons in ways we don't yet understand. Recent work suggests information does escape, perhaps through quantum correlations that violate classical expectations of independence. But the precise mechanism remains unclear. The information paradox sits at the intersection of quantum mechanics, general relativity, and thermodynamics. Resolving it will likely require quantum gravity, a theory we don't yet have. Until then, it remains a puzzle, a signpost pointing toward gaps in our understanding of reality's deepest laws. Asymptotic safety proposes that gravity becomes scale invariant at extremely high energies, making it mathematically well behaved. When physicists try to make general relativity quantum mechanical, they run into problems. Calculations give infinite answers, divergences that can't be removed by standard techniques. This is why quantum gravity is hard. But what if gravity, at extremely high energies, near the Planck scale, becomes scale invariant? What if it reaches a fixed point where the strength of gravitational interactions doesn't change with energy? This is the asymptotic safety proposal. It suggests that quantum gravity is well defined at all energy scales, including infinite energy, because interactions reach a stable configuration at high energies. The theory doesn't break down, it simply approaches a limiting behavior. If true, asymptotic safety would mean general relativity can be quantized without introducing new structures like strings or extra dimensions. It would be a more conservative approach, keeping Einstein's theory but understanding its quantum properties more deeply. Evidence for asymptotic safety comes from calculations in simplified models of gravity. They show hints of the required fixed point, but extending this to full quantum gravity in our universe is difficult, and the evidence is still incomplete. Asymptotic safety is less popular than string theory, or loop quantum gravity, but it's a serious contender. It suggests that gravity might be fundamentally simple, that the equations Einstein wrote down might work at all scales if we understand their quantum structure correctly. It's an optimistic vision. No need for radical departures, no hidden dimensions, no exotic structures. just gravity, properly quantized, behaving nicely all the way up to infinite energy. Whether nature agrees remains to be seen. Gravitational collapse might create exotic objects like gravastars, where dark energy supports a shell against complete collapse. What if black holes aren't the only endpoint of gravitational collapse? What if there are alternatives, objects that look like black holes from outside but have fundamentally different interiors? Gravastars, gravitational vacuum stars, are one such proposal. The idea is that during collapse, when matter approaches the density where a black hole would form, dark energy or some exotic form of matter creates outward pressure, halting the collapse just before an event horizon forms. The result would be a shell of ultra-dense matter surrounding a core of dark energy or exotic vacuum. From outside, it would appear almost identical to a black hole, same mass, same gravitational field. But there's no singularity, no event horizon. The interior is different, supported against further collapse by outward pressure. Gravastars are speculative. We have no evidence they exist, and their stability is uncertain. They require exotic matter or unusual quantum effects we're not sure are possible, but they're allowed by general relativity's equations under certain assumptions. Other alternatives exist too. Boson stars, held up by quantum pressure, fuzzball black holes from string theory, and various other exotic compact objects that might mimic black holes without actually being them. The challenge is distinguishing these from real black holes. If the differences are confined to the interior, hidden behind a surface that looks like an event horizon from outside, detecting them is nearly impossible with current technology. But future gravitational wave observations might reveal subtle differences, how these objects ring when disturbed, how they merge, how they interact, and nature might surprise us. What we call black holes might be more diverse, stranger than we imagine. The cosmological horizon limits what we can ever observe. As distant regions recede faster than light can travel, the universe is expanding, and that expansion is accelerating. This means distant galaxies are receding from us, and the farther away they are, the faster they recede. Eventually, there's a distance where galaxies recede faster than the speed of light. This doesn't violate relativity. Space-time itself is expanding, carrying galaxies with it. Light from those galaxies still travels at light speed through space, but the space between us and them is stretching faster than light can cross it. This creates a cosmological horizon. Galaxies beyond this horizon are receding so fast that their light will never reach us. Not now. Not ever. We can't see them. We can't communicate with them. They're beyond our observable universe, not just now, but for all future time. Worse, the horizon is shrinking. Galaxies we see today will eventually cross the horizon as acceleration carries them away. We're watching the night sky fade. In the far future, if intelligent beings exist in our galaxy, they'll see almost nothing, just our local group of galaxies, isolated in darkness. And there are galaxies we see now whose future light will never reach us. We're seeing their past, but we've lost access to their present. They're already beyond the horizon. We just don't know it yet because we're seeing light. They emitted billions of years ago, before they crossed over. The cosmological horizon is a boundary of knowledge. Beyond it, events happen that we cannot observe, as that cannot affect us. that are forever sealed off. The universe is larger than we can ever see, and it's getting more isolated with every passing moment. Quantum fluctuations of the gravitational field might impose a fundamental limit on how precisely we can measure space-time. Heisenberg's uncertainty principle says you can't simultaneously know a particle's position and momentum with perfect precision. Measure one more precisely, and the other becomes fuzzier. It's a fundamental limit, not a technical one. Might there be a similar limit for space-time itself? If space-time is quantum mechanical, if it fluctuates at the smallest scales, then perhaps you can't measure its geometry with perfect precision. At the Planck scale, about 10 to the power of minus 35 meters, quantum fluctuations of space-time become significant. Yet trying to measure distances more precisely than this might be meaningless, not because our instruments aren't good enough, but because space-time itself is uncertain at that scale. Some quantum gravity theories predict this. Space-time might be foamy at Planck scales, fluctuating wildly, making precise geometry impossible. You could know the large-scale curvature, but at tiny scales geometry becomes fuzzy, probabilistic. This would have profound implications. It would mean space-time isn't a smooth manifold all the way down. It would mean classical geometry emerges from quantum fuzz. It would mean there's a smallest meaningful distance, a limit to how finely we can probe space itself. Experimentally testing this is incredibly difficult. Planck-scale effects are far beyond current technology. Yeah, but physicists look for indirect signatures, tiny violations of Lorentz invariance, subtle changes in how particles propagate that might reveal space-time's quantum nature. If space-time fluctuates quantum mechanically, then the stage on which physics plays out is itself uncertain, probabilistic, subject to quantum rules. Even the geometry of reality isn't fixed. It's a quantum wave of possibilities, only becoming definite when observed at larger scales. The landscape problem in string theory suggests there may be 10 to the power of 500 possible vacuum states, each with different gravitational properties. String theory, one of the leading candidates for quantum gravity, has a problem: too many solutions. The equations allow an enormous number of different vacuum states, configurations of extra dimensions, fields, Born energies, each corresponding to a different possible universe with different physical constants. Estimates suggest 10 to the power of 500 possibilities. That's not 500. That's 10 to the power of 500, a number so large it defies comprehension. More possible universes than particles in the observable universe, raised to the power of itself, many times over. Each of these vacua would have different gravitational strength, different particle masses, different forces. Most would be inhospitable to life, to stars, to any structure. But among that vast landscape, there are presumably vacua like ours, with gravity tuned just right. This landscape makes predictions difficult. If every possible universe exists somewhere in the multiverse, how do we predict which one we're in? The theory doesn't single out our vacuum uniquely. It just says we must be in one that allows observers to exist, the anthropic principle again. Some see this as a failure of string theory, a theory that predicts everything, predicts nothing. Others see it as honest. Maybe the universe's constants aren't uniquely determined. Maybe the landscape is real, and we're one possibility among countless others. the landscape problem is unsolved. It challenges string theory's predictive power and raises deep questions about what we should expect from a fundamental theory. Should it uniquely predict our universe, or is the diversity of possibilities itself a prediction, a multiverse rich with variation? Gravitational collapse might create baby universes that branch off from our own through quantum tunneling events. What happens at a black hole singularity? General relativity predicts infinite curvature, but perhaps something else occurs, something quantum, something creative. One speculative idea: the collapsing matter doesn't just crush to a point. Instead, it quantum tunnels into a new, expanding region of space-time, a baby universe, disconnected from ours, growing into its own cosmos. From our perspective, it's a black hole. We see the event horizon, the matter disappearing. But from inside, on the other side of the horizon, space-time might be expanding, creating a new universe with its own space, time, and perhaps its own physical laws. These baby universes would be completely sealed off. No signals could pass between them and us. They'd exist independently, forever beyond observation or influence. They'd be separate realities, branching from ours at moments of gravitational collapse. If true, every black hole could spawn a universe. The cosmos might be far vaster than we imagine, not just our observable universe, not just a multiverse of parallel possibilities, but a tree of branching universes, each birthed from black holes in the generation before. This is highly speculative. It requires quantum gravity, and we don't have that theory yet. It makes no testable predictions. Baby universes are forever beyond our reach, but it's allowed by quantum cosmology models, a possibility lurking in the equations. It's a dizzying thought. Black holes not as endpoints but as beginnings. Collapse not as destruction but as creation. And our own universe, perhaps, born from a black hole in some parent cosmos, continuing an infinite lineage of gravitationally created realities. We still don't know why gravity is so weak compared to other forces, a mystery called the hierarchy problem. Gravity is weak, astonishingly, preposterously weak. A small magnet overcomes the gravitational pull of the entire Earth to lift a paperclip. The electromagnetic force holding atoms together is about 10 to the power of 36 times stronger than gravity at the atomic scale. Why? Why is gravity so much weaker than the other fundamental forces? This is the hierarchy problem, and it's one of the deepest mysteries in physics. The disparity is so vast, 36 orders of magnitude, that it seems to demand an explanation. Such extreme differences in nature usually point to something deeper. Some theories propose extra dimensions. Maybe gravity spreads into additional spatial dimensions we don't perceive, diluting its strength in our three-dimensional world. Other forces might be confined to our dimensions, keeping them strong. Other theories suggest supersymmetry or new particles that naturally generate the hierarchy through quantum corrections. Still others propose that what we call the Planck scale, where gravity becomes strong, isn't fundamental but emerges from deeper physics. Experiments at particle accelerators search for evidence of these explanations. So far, nothing. The hierarchy remains unexplained. Gravity stays stubbornly weak, offering no clues about why. Maybe it's just a brute fact, a number the universe chose without deeper reason. Or maybe it's a vital clue, pointing toward physics beyond our current theories, extra dimensions, quantum gravity, or principles we haven't imagined. For now, gravity remains the gentlest force, shaping galaxies and bending light, and yet barely noticeable at human scales. Its weakness allows complexity, allows structures, allows us. Perhaps that's not a mystery to solve, but a gift to appreciate. Gravity strong enough to build worlds, but weak enough to let life flourish within them. And so we reach the end of our journey through gravity. 100 facts, 100 windows into the force that shapes everything. We began with the simple: apples falling, planets orbiting, the pull you feel standing on solid ground. We moved through Einstein's revelation that gravity isn't a force at all, but the curvature of space-time itself. We explored black holes, neutron stars, gravitational waves, gravity at its most extreme, warping reality into forms that challenge comprehension. And we ended in mystery. The information paradox, quantum gravity, the hierarchy problem. Questions that remain open. Puzzles that point toward physics we don't yet understand. This is where we are now, not at the end of discovery, but somewhere in the middle, with glimpses of truth and vast territories still unmapped. Gravity connects everything. It holds you to the Earth to the sun to the galaxy, galaxies to each other across the cosmos. It's the weakest force, yet it reaches farthest. It's the simplest, just mass-curving space, yet it leads to the most complex questions about the nature of time, information, and reality itself. Perhaps what's most remarkable is this: we understand gravity well enough to navigate spacecraft across the solar system, to detect waves from colliding black holes a billion light-years away, to map the universe's history back to its first moments. And yet we still don't fully understand what gravity is, whether space-time is fundamental or emergent, whether singularities are real, why it's so weak. Science is like this. Every answer reveals new questions. Every solved mystery uncovers deeper ones. And that's not failure. That's the promise of infinite wonder, layer upon layer, always more to discover. So rest now. Let these ideas settle, drift, dissolve into sleep. Gravity will still be there tomorrow, patiently holding the world together, curving space-time around every mass, connecting you to everything across the infinite web of forces and fields that make up the cosmos. Thank you for wandering through these ideas with me tonight. May your dreams be gentle, your rest be deep, and may you wake tomorrow with a sense of the universe's quiet, persistent wonder still lingering. Good night.